Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's middle chapter, the Mesozoic era, when our planet wore a face both ancient and strangely familiar. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The Earth breathes differently now. It is 252 million years ago, and the planet stirs from the greatest dying it has ever known. The Permian extinction has claimed 9/10 of all marine species and 7/10 of terrestrial vertebrates, leaving behind a world scrubbed nearly clean of complex life. Yet in this apparent emptiness lies the seed of something magnificent. The Mesozoic era begins not with fanfare, but with the quiet persistence of survivors. Pangea stretches across the globe like a vast, unbroken skin of rock and sediment. From space, Earth appears almost monotonous, one enormous landmass surrounded by the single ocean called Panthalassa. The supercontinent spans from pole to pole, its interior baking under relentless sun, its coasts lapped by waves that have traveled unimpeded around the world. There are no familiar shapes here, no Atlantic or Pacific as we know them, just the endless curve of Pangea's shoreline and the immensity of the global sea. The landmass itself dwarfs any modern continent, stretching roughly 13,000 kilometers from north to south and 5,000 kilometers at its widest point, a continental giant that makes today's Asia look modest by comparison. The climate settles into patterns that will persist for millions of years. Without polar ice caps to reflect sunlight, Earth absorbs heat with patient efficiency. Atmospheric carbon dioxide concentrations hover at levels 3 to 5 times higher than today's measurements, creating a greenhouse effect that bathes even the poles in warmth. The global temperature differential between equator and poles has collapsed to just a few degrees, a thermal monotony that speaks to the extraordinary heat-trapping capacity of this ancient atmosphere. Palm trees will eventually grow where Antarctica now lies frozen, though that transformation unfolds across geological time with the pace of continental drift itself. The ocean currents flow in patterns both alien and strangely logical. Without the barriers of separate ocean basins, Panthalassa's waters circulate in vast, unbroken gyres. The Tethys Sea, that ancient predecessor to the Mediterranean, begins as a shallow embayment on Pangea's eastern shore, its warm waters already nurturing the coral reefs and marine communities that will define Mesozoic ocean life. The temperature gradient from surface to deep water remains gentler than in modern oceans, allowing tropical conditions to penetrate to depths that today remain perpetually cold. In this early Triassic world, life clings to the margins with remarkable tenacity. Small therapsids, the mammal-like reptiles that survived the great dying forage through landscapes of red stone and sparse vegetation. Lystrosaurus, a sturdy herbivore the size of a pig, has inherited the Earth almost by default, its fossils scattered across continents that were then pressed together like puzzle pieces. This unprepossessing creature, with its distinctive tusks and barrel-shaped body, comprises nearly 90% of all terrestrial vertebrate fossils from the earliest Triassic. Only took the near extinction of everything else for it to find its moment in the sun. The vegetation tells a story of patient recovery and fundamental change. Seed ferns and conifers begin to recolonize the empty landscapes. their root systems slowly binding soil that erosion has scattered like dust across the continents. The absence of complex forest ecosystems has left vast areas exposed to wind and rain, creating the characteristic red beds of iron oxide that paint Triassic rocks in russet hues. These are the deposits that will one day form the painted deserts of the American Southwest, the red sandstones of Britain, the colorful badlands of Argentina. The Earth is writing its autobiography in sediment and stone, each layer a page in the great book of deep time. Rivers flow red with iron oxides, carrying the oxidized remains of a world still learning to breathe again. The water courses through channels carved into bedrock exposed by the dying of forests, creating meandering patterns that speak to a landscape unanchored by extensive root systems. These ancient waterways deposit their iron-rich sediments in broad floodplains, where occasional fossil bones of the first Triassic creatures lie waiting for discovery by paleontologists still 250 million years in the future. The atmosphere itself bears witness to the planet's slow recovery. Oxygen levels, which plummeted during the Permian extinction, begin their gradual climb back toward levels that can support large, active animals. The ratio of oxygen isotopes preserved in marine carbonates hints at ocean chemistry still rebalancing itself after the acidification events that marked the Great Dying. Sulfur isotope signatures suggest continued volcanic outgassing from the Siberian traps, those massive basaltic provinces whose eruptions may have triggered the extinction in the first place. Mystery hangs in the air like morning mist, drifting through every aspect of this ancient world. Scientists still debate what precisely triggered the Permian extinction, whether it was the massive Siberian traps volcanism, oceanic acidification, hydrogen sulfide poisoning from bacterial blooms, or some combination of catastrophes that reset the biological clock. The evidence lies buried in rock layers, in isotope ratios, in the sudden disappearance of fossil forms that had thrived for millions of years. The boundary itself, that thin line in the rock that marks the end of the Paleozoic and the beginning of the Mesozoic, holds secrets that continue to elude complete understanding. The Earth keeps its secrets well, revealing them only to those patient enough to read stone-like scripture. Yet already, in these quiet early Triassic landscapes, evolution has begun its next great experiment. Small archosaurs. The ruling reptiles scurry through the undergrowth, their hip joints and ankle bones carrying the genetic blueprints for giants. Archosaurus itself, the namesake of this group, measures less than 3 meters in length, its crocodile-like form betraying no hint of the tremendous diversity it will spawn. These early archosaurs possess a suite of anatomical innovations, improved ankle joints that allow more efficient locomotion, modified hip sockets that will eventually enable some lineages to walk upright, and refined respiratory systems that hint at the high-energy lifestyles of their descendants. They do not know they are rehearsing for the age of dinosaurs. They simply live, breathe, reproduce, and die, each generation adding its small contribution to the vast symphony of change that will transform Earth into a world of titans. Their fossilized footprints, preserved in the red mudstones of Triassic river systems, show the characteristic gait of animals still learning to master terrestrial locomotion in a world recovering from near emptiness. The night sky above this ancient world would appear familiar, yet subtly different. The moon hangs closer to Earth, its gravitational pull creating tides more extreme than those of today. The length of an Earth day measures approximately 22.5 hours. The planet's rotation slowed by tidal friction over the intervening hundreds of millions of years. Star patterns remain unrecognizable. The constellations that will guide future navigators lie scattered across different portions of the celestial sphere, their light reaching Earth from angles that speak to our solar system's patient journey around the galactic center. The Mesozoic has begun with a whisper, not a roar. In the vastness of geological time, 185 million years stretches ahead like an unwritten book. The age of reptiles unfolds with the patience of stone itself. Each millennium, a single heartbeat in Earth's long dream of transformation. What began in the emptiness following catastrophe will become the most remarkable expansion of terrestrial life our planet has ever witnessed. But that story waits in the sediments ahead, patient as the stone that preserves it. The fractures begin as whispers in stone. Deep beneath Pangea's seemingly solid surface, the Earth's mantle convects with patient determination, carrying heat from the planet's molten core toward the surface in currents that move like geological blood. These convection cells have been building pressure for millions of years, and now, in the Middle Triassic, approximately 220 million years ago, the supercontinent begins to acknowledge what the deep Earth has long demanded: separation. The initial rifting occurs along zones of weakness that date back to Pangea's original assembly. When the earlier supercontinents, Laurasia and Gondwana, collided to form this massive landmass, they created suture zones, geological scars where different crustal blocks were welded together under tremendous pressure. Now these ancient wounds begin to reopen, following the paths of least resistance, like water finding its way downhill. The process unfolds with a slowness that defies human comprehension, measured not in years or decades, but in millions of years of patient geological work. The first cracks appear in what will one day become the central Atlantic Ocean. Here, along the eastern margins of what geologists will call Laurasia, the continental crust begins to thin and stretch. Magma from the mantle rises through these zones of extension, creating the earliest basaltic intrusions that herald the birth of a new ocean basin. The process resembles the slow tearing of an enormous piece of fabric, with the edges gradually pulling apart while the middle remains intact. Only took a few million years for the Earth to decide that the largest landmass in its history needed to be divided. The early stages of rifting manifest as broad, shallow valleys that extend for hundreds of kilometers across the continental interior. These rift valleys collect sediments eroded from the surrounding highlands, creating the characteristic red sandstones and mudstones that will preserve the footprints and fossils of Triassic life. The Connecticut River Valley, the Gettysburg Basin, the Culpeper Basin. These are the geological descendants of those ancient rift systems, their rocks still bearing witness to Pangea's slow dissolution. Volcanic activity accompanies the rifting process with sporadic intensity. Basaltic lava flows pour across the landscape, creating dark layers within the predominantly red Triassic sediments. These volcanic episodes occur in pulses separated by thousands of years, each one adding to the growing body of evidence that the supercontinent has begun its inexorable journey toward fragmentation. The lava flows cool and crystallize into columnar basalt formations, their hexagonal columns standing like geological organ pipes across the ancient landscape. The climate during this period of initial rifting remains remarkably stable, a testament to Pangea's massive thermal inertia. The interior of the supercontinent continues to experience extreme seasonal temperature variations, with scorching summers and surprisingly cold winters creating desert conditions across vast expanses of the continental heartland. Yet along the emerging rift valleys, slightly more moderate conditions prevail. The topographic relief created by the rifting process generates local weather patterns that concentrate precipitation and create oases of relatively lush vegetation. Lakes form in the deepest portions of the rift valleys, their waters sometimes fresh, sometimes saline depending on the local hydrology and climate. Lake Lokotong and Lake Passaic represent the geological memory of these ancient water bodies, their laminated sediments preserving exquisite fossils of early dinosaurs, primitive crocodilians, and a variety of fish species that adapted to life in these isolated aquatic environments. The lake sediments also preserve pollen and spores that document the gradual recovery and diversification of plant communities following the Permian extinction. The earliest dinosaurs make their appearance during this period of continental reorganization, though they remain relatively small and unspecialized compared to their later descendants. Eoraptor, discovered in the late Triassic rocks of Argentina, measures only about 1 meter in length and displays a mixture of primitive and derived characteristics that place it near the base of the dinosaur family tree. These early dinosaurs occupy ecological niches as generalized predators and omnivores, competing with other archosaurs for resources in ecosystems still recovering from the Great Extinction. Mystery surrounds the precise mechanisms driving Pangea's breakup. While geologists understand that mantle convection provides the ultimate driving force, the specific triggers for the timing and location of rifting remain subjects of ongoing research. Some evidence suggests that the massive volcanism of the Siberian traps may have disrupted global mantle flow patterns, contributing to the instability that led to Pangea's fragmentation. Other theories propose that the supercontinent's own thermal properties, its tendency to act as an insulating blanket over the mantle, created the conditions for its own destruction. The process of continental rifting creates its own unique geological signatures. The rocks formed during this period display characteristic features: normal faults that drop blocks of crust downward, creating the graben structures that define rift valleys, volcanic dikes that cut across existing rock formations like frozen rivers of magma, and sedimentary sequences that record the gradual deepening and widening of the rift basins. These geological markers allow modern scientists to reconstruct the timing and progression of Pangea's breakup with remarkable precision. Marine incursions begin to penetrate the most advanced rift systems, bringing seawater into basins that had previously been occupied by freshwater lakes. The transition from continental to marine environments creates distinctive sedimentary sequences that record the gradual opening of new ocean basins. Evaporate deposits layers of salt and gypsum formed by the evaporation of trapped seawater mark the earliest stages of ocean formation. When narrow seaways connected the developing rift valleys to the global ocean system, the fauna and flora of the rift valleys display remarkable diversity despite the relatively small geographic extent of these environments. Phytosaurs large, crocodile-like archosaurs dominate the aquatic predator niches, their elongated snouts perfectly adapted for catching fish in the shallow waters of Rift Valley lakes. Atosaurs, heavily armored herbivorous archosaurs, browse on the vegetation that flourishes along the water margins. Early mammals, still tiny and nocturnal, scurry through the underbrush, their presence known primarily from their distinctive teeth preserved in the fossil record. The breakup of Pangea represents one of the most significant geographical reorganizations in Earth's history, yet it unfolds with a deliberate slowness that speaks to the immense scales of geological time. The initial rifting phase will continue for tens of millions of years before true oceanic crust begins to form between the separating continental blocks. Each millimeter of extension, each volcanic eruption, each sedimentary layer deposited in the growing rift valleys contributes to a transformation that will ultimately create the Atlantic Ocean and reshape the geography of an entire planet. The Earth dreams of new configurations, its solid surface belying the molten restlessness below. What appears permanent and unchanging on human timescales reveals itself as fluid and dynamic when viewed through the lens of deep time. Pangea's fracture lines spread like cracks in ice, following paths determined by physics and geology rather than the preferences of the life forms that inhabit the surface. The supercontinent has begun its patient journey toward dissolution, each day bringing imperceptible changes that accumulate into transformations of continental magnitude. The red Earth stretches endlessly under a copper sky. It is the late Triassic, approximately 210 million years ago, and Pangea's interior has become a vast expanse of desert punctuated by meandering rivers that carry life through landscapes otherwise too harsh for complex ecosystems. The supercontinent's heart beats slowly, its pulse measured in the seasonal flooding of ancient waterways that wind through badlands painted in every shade of rust and ochre. The climate has settled into patterns of stunning extremity. Summer temperatures in Pangea's interior soar beyond what any modern desert experiences, with ground temperatures reaching levels that would prove lethal to most contemporary life forms. Yet the planet's high atmospheric carbon dioxide content creates a greenhouse effect so pronounced that even winter temperatures rarely drop below freezing, except at the highest elevations and most poleward latitudes. The result is a world of perpetual warmth, punctuated by seasonal droughts that last for months, broken only by brief but intense periods of monsoonal rainfall. These red beds, the Chinle Formation of the American Southwest, the Murcia Mudstone of Britain, the Santa Maria Formation of Brazil represent the accumulated sediments of vast alluvial plains where rivers deposited their iron-rich loads across continental lowlands. The distinctive coloration comes from iron oxides that formed under the oxidizing conditions prevalent during sediment transport and deposition. Each layer tells a story of seasonal flooding and drying, of rivers that swelled with monsoon rains and then dwindled to chains of isolated pools during the long dry seasons. The rivers themselves follow courses dictated by the gentle slopes of the continental interior and the growing influence of the early rift systems that herald Pangea's eventual breakup. These waterways meander across the landscape with the lazy complexity of mature river systems, creating extensive floodplains that support ribbons of vegetation in an otherwise arid world. The Chinle paleorivers, preserved in the rock record of the American Southwest, show evidence of channels hundreds of meters wide carrying tremendous volumes of water during peak flow periods. Along these ancient waterways, life congregates with an intensity born of necessity. The rivers serve as linear oases, supporting diverse ecosystems that would be impossible in the surrounding deserts. Massive conifers. Early relatives of modern monkey puzzle trees and Norfolk pines line the riverbanks, their tall trunks and umbrella-shaped crowns creating patches of shade in landscapes otherwise dominated by low shrubs and hardy ferns. These Araucarioxylon trees grow to heights exceeding 40 meters, their fossilized trunks now forming the spectacular petrified logs of Arizona's petrified forest. The understory beneath these coniferous giants harbors a complex community of plants that represent evolutionary experiments in drought tolerance and water conservation. Cycads and cycadioids, seed plants that superficially resemble palms but belong to an entirely different evolutionary lineage, dominate the middle canopy with their distinctive crowns of divided leaves. These plants have perfected strategies for surviving in environments where water availability fluctuates dramatically between wet and dry seasons, storing water in enlarged stems and developing waxy leaf coatings that minimize moisture loss. Ferns carpet the forest floor where sufficient moisture persists, their delicate fronds creating an understory of surprising lushness beneath the drought-adapted canopy above. Yet, these are not the familiar ferns of modern temperate forests. Many Triassic species display adaptations to arid conditions that seem almost contradictory to their fundamental dependence on water for reproduction. Some develop succulent-like stems for water storage, while others produce spores with enhanced resistance to desiccation. Only took a few million years of drought to teach even the most water-dependent plants new tricks. The fauna of these riverine corridors displays remarkable diversity and includes some of the most spectacular creatures in Earth's history. Phytosaurs patrol the waterways like living submarines, their elongated snouts and powerful tails perfectly adapted for aquatic predation. Desmatosuchus, an etosaur reaching lengths of 5 meters, browses along the riverbanks, its body encased in bony armor plates that would not look out of place on a modern armadillo scaled up to rhinoceros size. These heavily protected herbivores represent one of evolution's early experiments with comprehensive body armor, their fossil remains showing evidence of sophisticated social behaviors and possibly even parental care. The first true dinosaurs make their appearance in these late Triassic ecosystems, though they remain relatively small and occupy specialized ecological niches rather than dominating the landscape as they will in later periods. Coelophysis, a slender theropod measuring up to 3 meters in length, hunts in packs along the river margins, its lightweight build and grasping hands making it an efficient predator of small vertebrates and possibly fish. Fossil evidence from Ghost Ranch in New Mexico suggests that these early dinosaurs sometimes engaged in cannibalistic behavior, perhaps during periods of environmental stress when preferred prey became scarce. Plateosaurus and other early sauropodomorphs browse on vegetation in the river valleys, their long necks allowing them to reach high into the coniferous canopies for foliage unavailable to other herbivores. These early giants, reaching lengths of up to 10 meters, represent the first of the truly large dinosaurs, yet they retain the ability to walk on their hind legs when necessary, a behavioral flexibility that their later descendants will abandon in favor of obligate quadrupedalism. Mystery pervades every aspect of these ancient ecosystems, from the precise mechanisms that allowed such large animals to survive in seemingly harsh environments to the evolutionary pressures that drove the rapid diversification of Archosaurian reptiles during this period. The fossil record preserves tantalizing glimpses of behaviors and ecological relationships that challenge our understanding of how complex ecosystems function under climatic conditions unlike anything in the modern world. The preservation of these late Triassic ecosystems creates one of paleontology's great ironies. Some of the most complete fossil assemblages in Earth's history come from environments that were periodically catastrophic for the organisms living in them. Sudden flooding events buried entire communities in sediment, creating fossil bone beds of extraordinary richness and diversity. The famous Coelophysis quarry at Ghost Ranch preserves hundreds of individuals in a single layer, suggesting a mass mortality event that eliminated an entire population but simultaneously created an unparalleled window into late Triassic ecology. The sedimentology of these deposits reveals the complex interplay between climate, hydrology, and ecosystem dynamics that characterized late Triassic environments. Paleosol horizons. Ancient soil layers preserve evidence of root systems, burrows, and chemical weathering patterns that document the gradual adaptation of terrestrial ecosystems to increasingly arid conditions. Trace fossils including dinosaur trackways, coprolites, and invertebrate burrows provide insights into behavior and ecology that skeletal remains alone cannot offer. The plant fossil record from these environments preserves not only the obvious large specimens like petrified tree trunks, but also delicate reproductive structures, leaves, and even pollen grains that document the evolutionary innovations that allowed plant communities to colonize increasingly dry landscapes. The development of more efficient water transport systems, improved seed dispersal mechanisms, and enhanced drought tolerance represents one of the great adaptive radiations in plant evolutionary history. Seasonal cycles governed every aspect of life in these ancient river systems. During the wet season, when monsoonal rains recharged the water table and filled the rivers to capacity, The ecosystems burst into activity reminiscent of modern African savannas during the rains. Breeding seasons for most vertebrates coincided with peak water availability, ensuring that vulnerable young animals had access to abundant food and water during their critical early development. The dry season told a different story entirely. As water levels dropped and many tributaries dried up completely, animal populations concentrated around the remaining permanent water sources. Competition intensified, predation pressure increased, and many species entered dormancy or migrated to more favorable areas. The fossil record suggests that some late Triassic vertebrates developed behavioral and physiological adaptations similar to those seen in modern desert animals' estivation, water conservation, and the ability to survive on metabolic water derived from food. These red desert landscapes represent one of Earth's great experiments in continental-scale aridity, a preview of the even more extreme conditions that will characterize parts of the Jurassic and Cretaceous periods. Yet within this apparent harshness lies evidence of life's remarkable adaptability and the power of water to create oases of biological diversity even in the most challenging environments. The legacy of these late Triassic river systems lives on in the fossil record, their sediments preserving a world both alien and beautiful, harsh yet teeming with evolutionary innovation. The sky darkens with an ominous permanence. It is the end of the Triassic period, approximately 201 million years ago, and Earth trembles under the weight of its own restless interior. Deep beneath what will one day become the Atlantic Ocean floor, mantle plumes surge upward with unprecedented force, carrying molten rock toward the surface in a geological uprising that will fundamentally reshape the planet's biological and atmospheric systems. The Central Atlantic Magmatic Province begins its catastrophic birth with volcanic violence that dwarfs any eruption in human experience. Across 4 continents, North America, South America, Europe, and Africa, massive fissures open in the Earth's crust, releasing torrents of basaltic lava that spread across the landscape like molten seas. These are not the conical volcanoes of popular imagination, but rather vast flood basalts that emerge from linear vents stretching for hundreds of kilometers across the fragmenting supercontinent. The scale of the eruptions defies comprehension. Modern estimates suggest that the Central Atlantic Magmatic Province covered approximately 11 million square kilometers at its peak extent, making it one of the largest volcanic events in Earth's history. Individual lava flows extend for hundreds of kilometers from their source vents, creating basaltic plains that bury entire ecosystems under layers of cooling rock. The Palisades Sill along the Hudson River, the Gettysburg Sill in Pennsylvania, the vast flood basalts of Morocco, these represent mere fragments of a volcanic province that once spanned continents. The atmospheric consequences of such massive volcanism unfold with terrifying efficiency. Each cubic kilometer of erupted basalt releases enormous quantities of carbon dioxide, sulfur dioxide, hydrogen sulfide, and other volcanic gases into the atmosphere. The sulfur compounds create acid rain that acidifies soils and water bodies across vast regions, while carbon dioxide concentrations spike to levels that drive global temperatures upward by several degrees. The combination creates a greenhouse effect so intense that polar ice caps, already absent in the Triassic greenhouse climate, would be impossible to maintain even if temperatures were to drop significantly. Yet paradoxically, the initial effects of the volcanism may actually cause temporary cooling rather than warming. Sulfur dioxide emissions react with water vapor in the upper atmosphere to form sulfuric acid aerosols that reflect incoming solar radiation back to space. This volcanic winter effect can persist for years following major eruptions, creating a period of global cooling that disrupts ecosystems already stressed by the longer-term warming trend caused by increased carbon dioxide levels. The marine realm suffers particularly catastrophic disruption as oceanic chemistry shifts dramatically in response to the volcanic outgassing. Ocean acidification occurs as carbon dioxide dissolves into seawater, forming carbonic acid that lowers the pH of marine environments to levels toxic to many organisms, particularly those with calcium carbonate shells or skeletons. Coral reefs, which had begun to recover and diversify following the Permian extinction, experience another devastating collapse as the very water they live in becomes too acidic to support their calcium carbonate skeletons. Atmospheric mercury concentrations spike to toxic levels as volcanic emissions release this heavy metal into the global circulation system. Mercury poisoning affects both terrestrial and marine food webs, with particular impact on organisms at higher trophic levels, where biomagnification concentrates the toxin to lethal doses. The mercury signature preserved in end Triassic boundary rocks provides modern geologists with one of the clearest chemical fingerprints of the massive volcanism that drove this extinction event. The terrestrial ecosystems of late Triassic river valleys and coastal plains face a multi-pronged assault that few species can survive. Acid rain strips nutrients from soils and poisons water sources, while temperature fluctuations stress plants and animals adapted to the stable greenhouse conditions of the earlier Triassic. The massive dinosaurs that had begun to diversify during the late Triassic find their food webs collapsing as plant communities succumb to the toxic atmospheric conditions. Many of the iconic late Triassic archosaurs disappear forever during this crisis. The heavily armored pterosaurs, which had achieved remarkable diversity and occupied herbivorous niches across Pangea, vanish completely from the fossil record. Phytosaurs, those crocodile-like semi-aquatic predators that had dominated freshwater ecosystems, also disappear entirely. The extinction removes entire ecological guilds, clearing evolutionary space for the dramatic dinosaur radiations that will characterize the Jurassic period. Only took one of the largest volcanic events in Earth's history to clear the stage for the Age of Giants. The timing of the extinction coincides so precisely with the volcanic activity that causation seems certain. Yet mysteries remain about the exact mechanisms that drove species to extinction. Some groups that might be expected to survive, such as early mammals with their small size and presumably high metabolic flexibility, suffer severe population bottlenecks. Other organisms, including some early dinosaur lineages, not only survive but apparently diversify rapidly in the immediate aftermath of the extinction. Plant communities undergo fundamental restructuring as entire families disappear and others expand into vacant ecological niches. The seed ferns that had dominated late Triassic floras vanish almost completely, while conifers and other gymnosperms begin the radiation that will make them the dominant plants of the Jurassic world. The extinction represents a major evolutionary filter that selects for particular physiological and ecological traits while eliminating others. Marine ecosystems face their own cascade of collapse and reorganization. Ammonites, those spiral-shelled cephalopods that had survived the Permian extinction and rediversified during the Triassic, suffer another major bottleneck that reduces their diversity to just a few surviving lineages. These survivors will found the spectacular ammonoid radiations of the Jurassic and Cretaceous, but their passage through the end Triassic crisis reduces one of the ocean's most diverse groups to a handful of species. The recovery from the end Triassic extinction follows patterns both familiar and unique. As with previous mass extinctions, the immediate aftermath sees the proliferation of disaster taxa opportunistic species that can rapidly colonize disturbed environments, but lack the specialized adaptations of the communities they temporarily replace. These early recovery faunas often display unusually small body sizes and simplified ecological structures compared to the complex communities that preceded the crisis. The geographic distribution of extinction and survival creates a patchwork pattern across Pangea that reflects both the direct effects of volcanism and the more subtle influences of climate and oceanographic changes. Areas closest to the major volcanic centers experience the most severe extinction, while some refuge areas maintain higher survival rates that become the sources for post-extinction radiations. The fossil record preserves evidence of the extinction in multiple forms: abrupt disappearances of diverse fossil assemblages, geochemical signatures of environmental crisis, and the distinctive rock layers formed by volcanic ashfalls and flood basalts. The boundary between Triassic and Jurassic rocks often appears as a sharp contact between fossil-rich late Triassic sediments and the overlying early Jurassic rocks that contain much simpler, lower diversity fossil assemblages. Ocean circulation patterns shift in response to the changing atmospheric composition and global temperature regime, creating new patterns of upwelling and deep water formation that will influence marine ecosystems for millions of years. The breakdown of late Triassic climate stability marks the beginning of the climatic oscillations that will characterize much of the later Mesozoic era. As the volcanic crisis gradually subsides and atmospheric chemistry begins to stabilize, the surviving lineages face a world profoundly different from the one their ancestors had inhabited. The extinction has reset the evolutionary clock, creating new opportunities for adaptive radiation while eliminating many of the ecological constraints that had limited diversification during the late Triassic. The stage is set for one of the most remarkable periods of evolutionary innovation in Earth's history, the Jurassic period, when dinosaurs will finally claim their throne as the dominant terrestrial vertebrates. The waters rise with geological patience. It is the early Jurassic, approximately 190 million years ago, and Earth begins one of the most dramatic marine transgressions in its recorded history. Sea levels climb steadily higher, driven by the thermal expansion of ocean water heated by continued volcanism and the displacement caused by new oceanic crust forming along the spreading centers of the fragmenting Pangea. What had been vast continental lowlands gradually disappears beneath warm, shallow seas that will reshape the planet's geography and biological communities for tens of millions of years. The scale of this marine transgression dwarfs anything witnessed during human civilization. Modern sea levels would need to rise by more than 200 meters to approach the high stand reached during the Middle Jurassic, submerging coastal plains hundreds of kilometers inland from present-day shorelines. The English countryside lies beneath tropical seas dotted with coral islands. Much of what will become the Great Plains of North America transforms into a vast epicontinental sea stretching from the Arctic Ocean to the Gulf of Mexico. The Tethys Ocean expands dramatically, creating a massive east-west seaway that nearly bisects the supercontinent. The mechanism driving this unprecedented sea level rise reflects the planet's continued adjustment to the breakup of Pangea. As new oceanic crust forms along the mid-ocean ridges, its elevated temperature causes it to occupy more volume than older, cooler oceanic crust. This thermal expansion of the oceanic crust effectively raises the floor of the ocean basins, displacing enormous volumes of seawater onto the continental margins. Additionally, the formation of large igneous provinces and submarine volcanic plateaus further reduces the volume available for ocean water, forcing sea levels ever higher. The rising seas create vast epiric seas, shallow marine environments that extend far into continental interiors. These inland seas rarely exceed depths of 50 meters, creating enormous areas of warm, well-lit marine habitat unlike anything that exists today. The Western Interior Seaway of North America, the Russian Platform Sea, the epicontinental seas of Europe and North Africa. These represent some of the largest shallow marine ecosystems in Earth's history. Their extent measured in millions of square kilometers of productive marine habitat. The water temperature in these tropical seas maintains remarkable warmth even at high latitudes. Paleoclimatic reconstructions suggest that ocean surface temperatures near the poles reached values comparable to modern tropical seas, creating a world where coral reefs flourish in what are now the frigid waters of the Arctic Ocean. The temperature gradient from equator to poles collapses to just a few degrees, eliminating the thermal barriers that restrict modern marine organisms to specific latitudinal bands. Ocean circulation patterns in this greenhouse world differ fundamentally from modern systems. Without significant polar ice caps to drive thermohaline circulation, ocean currents depend primarily on wind patterns and the Earth's rotation to create global circulation systems. The vast east-west extent of the Tethys Ocean allows equatorial currents to circulate completely around the globe, distributing heat with extraordinary efficiency and maintaining the thermal homogeneity that characterizes Jurassic marine environments. The chemistry of these ancient seas reflects both the elevated atmospheric carbon dioxide concentrations and the massive scale of submarine volcanism occurring along the expanding oceanic ridge systems. While ocean pH remains within ranges tolerable to most marine organisms, the elevated CO2 levels create carbonic acid concentrations that affect the ability of shell-forming organisms to precipitate calcium carbonate. Some marine groups adapt by developing thicker shells or alternative skeletal minerals, while others modify their physiology to function in the more acidic conditions. Marine productivity reaches extraordinary levels in these warm, nutrient-rich seas. The breakdown of thermal stratification allows nutrients from deep water to reach surface waters more easily, while the extensive shallow water areas provide enormous volumes of photic zone habitat where photosynthesis can occur. A coccolithophores, microscopic marine algae that produce calcium carbonate plates, begin their rise to dominance during this period. Their blooms so massive that they will eventually create some of the most extensive limestone formations in Earth's history. The fossil record of these Jurassic seas preserves evidence of marine ecosystems of stunning diversity and complexity. Ammonites, having survived the end Triassic extinction as just a few lineages, undergo an explosive adaptive radiation that produces hundreds of species with shell forms ranging from tightly coiled spirals to loosely coiled helixes to nearly straight cones. These cephalopods occupy ecological niches throughout the water column, from bottom-dwelling scavengers to active pelagic predators, their jet propulsion systems making them among the most sophisticated swimmers in Jurassic oceans. Belemnites, those squid-like cephalopods whose internal shells fossilize as bullet-shaped guards, proliferate throughout Jurassic seas as active predators. Unlike their modern squid relatives, belemnites develop massive internal shells that may have served as ballast to control buoyancy, allowing them to hover motionlessly in the water column while hunting for prey. Their fossilized ink sacs, occasionally preserved in extraordinary detail, contain melanin compounds chemically identical to modern cephalopod ink, suggesting behavioral continuity across hundreds of millions of years. Marine reptiles achieve sizes and diversity that dwarf their modern counterparts. Plesiosaurs develop two distinct body plans that will persist throughout the Mesozoic long-necked forms that use their flexibility to capture prey in complex three-dimensional movements, and short-necked pliosaurs that become the apex predators of Jurassic seas. Leadsichthys, a pachycormid fish, grows to lengths approaching 17 meters, making it one of the largest bony fish ever to exist, and a filter feeder comparable in size to modern baleen whales. The shallow epicontinental seas create vast areas of carbonate platform environments where coral reefs, stromatolites, and other biological constructions flourish. These reef systems differ significantly from modern coral reefs, dominated by groups like the rudists, large bivalves that develop complex internal structures and sometimes form extensive bioherm complexes. Hexacorals, the group that includes modern reef-building corals, begin their radiation during the Jurassic but share reef-building duties with a variety of other organisms, including bryozoans, hydrozoans, and various types of sponges. Mystery surrounds many aspects of these ancient marine ecosystems, particularly the mechanisms that maintained such high biodiversity in relatively uniform environmental conditions. Modern marine ecosystems achieve high diversity partly through environmental heterogeneity, different species occupying different temperature, depth, and chemical regimes. Yet Jurassic seas appear to have been remarkably homogeneous in their physical properties while supporting extraordinary biological diversity. The trace fossil record from Jurassic marine sediments reveals complex ecological interactions and behavioral patterns that flesh out the picture provided by body fossils. Boring traces in ammonoid shells document predator-prey relationships, while elaborate burrow systems in the seafloor sediments show the development of complex infaunal communities. Some trace fossils suggest cooperative behaviors or social interactions among marine organisms that have no modern analogues. Isotopic studies of Jurassic marine carbonates provide insights into ocean temperature, salinity, and productivity patterns that cannot be obtained from fossils alone. Oxygen isotope ratios confirm the warm, equable conditions suggested by fossil distributions, while carbon isotope excursions document periods of enhanced marine productivity and organic carbon burial that influenced atmospheric chemistry and global climate. The sedimentary rocks formed in these ancient seas preserve not only fossils but also detailed records of sea level fluctuations, storm deposits, and other environmental phenomena. Hard ground surfaces, sea floors that became lithified underwater due to slow sedimentation rates, preserve evidence of long periods of sediment starvation punctuated by episodic depositional events. These surfaces often show extensive boring and incrustation by marine organisms, creating complex ecological communities preserved in 3 dimensions. The geography of these flooded continents creates archipelago landscapes, where terrestrial organisms become isolated on islands surrounded by warm seas. This isolation drives evolutionary diversification among terrestrial groups, while the extensive marine connections facilitate the global distribution of marine species. The resulting biogeographic patterns show high endemism on land coupled with cosmopolitan distributions in the sea, a pattern that will characterize much of the later Mesozoic era. As sea levels reach their Jurassic maximum, the planet takes on an appearance unique in its history. Vast warm oceans dotted with coral islands and separated by narrow seaways rather than the broad continental masses that characterize earlier and later periods. This aquatic Earth provides the stage for evolutionary innovations that will influence marine ecosystems for the remainder of the Mesozoic era and beyond. Only took the breakup of a supercontinent to turn the planet into a world of shallow tropical seas where giants swim through waters warm as blood. The reefs grow with crystalline precision. It is the Middle Jurassic, approximately 170 million years ago, and the warm, shallow seas that have flooded much of Pangea's fragmenting landmasses become living cities of calcium carbonate. In the vast Tethys Ocean and the epicontinental seas that stretch across Europe, North America, and Northern Africa, coral reefs flourish with a diversity and architectural complexity that rivals the greatest reef systems in Earth's history. These ancient reefs differ fundamentally from their modern counterparts, dominated not by the familiar hexacorals that build today's tropical reefs, but by an extraordinary assemblage of organisms that have since vanished from the seas. Scleractinian corals share reef-building duties with massive stromatoporoid sponges, whose layered, dome-shaped skeletons create platform structures tens of meters across. Hydrozoans contribute delicate branching forms that add structural complexity to the reef framework, while bryozoans encrust available surfaces with their intricate colonial networks. The Tethys Ocean serves as the epicenter of reef development, its east-west orientation allowing tropical conditions to extend across vast longitudinal distances. Here, along the southern margins of the European archipelago and the northern coasts of the African continent, reef systems develop that will eventually be uplifted and exposed as the famous Jurassic limestones of southern Germany, the Cotswolds, and the Atlas Mountains. The individual reefs often exceed modern barrier reef systems in both size and complexity, creating carbonate platforms that extend for hundreds of kilometers along the ancient coastlines. Water clarity in these Jurassic seas reaches extraordinary levels due to the absence of terrestrial runoff across the flooded continental interiors. The epicontinental seas act as vast settling basins where suspended sediments drop out of the water column long before reaching the reef environments. This crystal-clear water allows photosynthetic organisms to flourish at depths greater than in modern oceans, creating reef systems that extend from the surface down to depths of 50 meters or more. The dominant reef builders display architectural innovations that seem to anticipate the engineering principles that will govern reef construction throughout the rest of Earth's history. Massive hexacorals develop complex internal structures that maximize surface area for their symbiotic algae while maintaining structural integrity against wave action. Some species create elaborate branching forms that trap sediment and organic matter, gradually building the reef framework upward and outward through a combination of biological construction and sediment binding. Rudist bivalves begin their remarkable evolutionary experiment during this period, developing asymmetrical shell forms that allow them to function as sessile reef builders despite their molluscan heritage. These unusual organisms abandon the typical bivalve lifestyle of filter feeding from within a protective shell, instead developing one valve into a cone-shaped foundation while the other becomes a lid-like operculum. The result resembles a horn coral more than a traditional clam, and these biological architects will eventually dominate many Cretaceous reef systems. The reef communities support extraordinary diversity in both their structural frameworks and their associated fauna. Crinoids. Sea lilies create underwater forests of feathery arms that filter plankton from the water column, while their calcareous stems contribute to the reef framework upon death. Some species develop stems over 20 meters long, creating kelp forest-like environments in these ancient tropical seas. The density of crinoid populations sometimes becomes so extreme that entire limestone formations consist almost entirely of disarticulated crinoid plates and stems. Marine reptiles patrol these reef systems as apex predators. Their fossil remains occasionally preserved within the reef framework itself. Cryptoclydus, a long-necked plesiosaur measuring up to 8 meters in length, uses its remarkable neck flexibility to probe crevices and caves within the reef structure for hidden prey. The extreme elongation of the neck, containing as many as 76 vertebrae, allows these marine reptiles to feed in ways impossible for their shorter-necked contemporaries. Ichthyosaurs cruise the open waters above the reefs, their dolphin-like body forms representing one of evolution's most successful experiments in aquatic adaptation. Ophthalmosaurus, with its enormous eyes adapted for deep water vision, suggests that some ichthyosaur species feed primarily in the low-light environments beneath and within the reef structures. The preservation of soft tissues in some ichthyosaur fossils reveals details of their physiology that confirm their status as fully aquatic, warm-blooded marine reptiles. The reef lagoons create protected environments where delicate organisms flourish away from the wave action that batters the reef fronts. Here, beds of seagrass. Analogues marine plants that have independently evolved grass-like growth forms provide nursery habitat for juvenile fish and invertebrates. The lagoon sediments accumulate as fine-grained limestones that preserve exquisite fossils of the smaller organisms that inhabit these protected environments. Ammonites reach peak diversity in the reef environments, with some species developing elaborate shell ornamentation that may have served both hydrodynamic and defensive functions. Cosmoceras displays intricate ribbing patterns and tubercles that create complex water flow around the shell, while Perisphinctes develops loosely coiled shells that allow for rapid growth and potentially enhanced jet propulsion. The ecological roles of these diverse ammonoids remain partially mysterious, though their abundance and variety suggest they occupied numerous niches throughout the reef ecosystem. The trace fossil record from Jurassic reef environments preserves evidence of complex behavioral interactions and ecological relationships. Boring traces in coral skeletons document the activities of various organisms that excavated living spaces within the reef framework, while incrustation patterns show how organisms competed for space on available hard surfaces. Some traces suggest coordinated behaviors or even primitive agriculture, where certain organisms may have cultivated algae or bacteria within their borings. Fish diversity explodes within these reef environments, with early representatives of many modern fish families appearing in the fossil record. Cretaceous, an early relative of modern bowfins, develops specialized feeding adaptations for crushing the shells of reef-dwelling invertebrates. Leptolepis, an early teleost, displays the advanced jaw mechanics that will make this group the dominant marine fish for the remainder of Earth's history. The variety of fish feeding strategies from coral polyp pickers to mollusk crushers to planktivorous filter feeders documents the complex trophic relationships that characterize mature reef ecosystems. Mystery shrouds many aspects of these ancient reef communities, particularly the mechanisms that maintain such high diversity in apparently stable environments. Modern reef systems achieve high species diversity partly through environmental fluctuations that prevent any single species from monopolizing resources. Yet Jurassic reefs appear to have developed in remarkably stable climatic conditions. The answer may lie in the three-dimensional complexity of the reef structures themselves, which created numerous microenvironments and ecological niches within relatively small geographic areas. The preservation potential of reef environments creates one of paleontology's great treasures, three-dimensional fossil communities that maintain the spatial relationships among organisms as they lived. Unlike most fossil assemblages, which represent transported and mixed remains from various environments, reef fossils often preserve ecological communities in their living positions. This allows paleontologists to reconstruct food webs, competitive interactions, and community structure with unprecedented detail. Geochemical studies of Jurassic reef carbonates reveal details of ancient ocean chemistry that cannot be obtained from other sources. Strontium isotope ratios document the balance between continental weathering and hydrothermal input from oceanic ridge systems, while rare earth element patterns provide insights into seawater composition and circulation patterns. These chemical signatures confirm the unusual ocean chemistry of the Jurassic greenhouse world and help explain the extraordinary productivity of reef ecosystems. The reef systems also serve as sensitive recorders of environmental change, their growth patterns documenting fluctuations in sea level, temperature, and ocean chemistry. Growth bands in coral skeletons preserve annual and even seasonal cycles, while changes in reef community composition mark longer-term environmental shifts. These biological archives provide detailed records of climate variability during one of Earth's most stable greenhouse periods. The carbonate factories of these Jurassic reefs operate with extraordinary efficiency, converting dissolved carbon dioxide and calcium ions into solid limestone at rates that rival modern tropical reefs despite the very different community composition. The total volume of carbonate rock produced during the Middle Jurassic represents one of the great peaks in biological limestone formation, creating deposits that will serve as aquifers, building stones, and geological archives for hundreds of millions of years. As these reef systems mature and expand, they create positive feedback loops that enhance their own growth and diversity. The three-dimensional framework they construct provides habitat for increasingly diverse communities of organisms, while the biological processes of the reef communities modify local water chemistry in ways that promote continued carbonate precipitation. The result is self-sustaining ecosystems that grow upward and outward through their own biological activity, creating some of the most productive and diverse marine environments in Earth's history. Only took a few million years of greenhouse conditions to turn shallow seas into crystal cities where ancient architects built monuments from their own skeletons. The forests stretch endlessly without a single bloom. It is the Middle Jurassic, approximately 160 million years ago, and Earth's terrestrial landscapes wear a cloak of green that would appear both familiar and profoundly alien to modern eyes. Vast coniferous woodlands carpet the continents, their canopies dominated by towering araucarias, primitive pines, and cycads that create cathedral-like spaces beneath their spreading branches. Yet, in all this verdant abundance, not a single flower exists. The angiosperms remain tens of millions of years in the future, leaving these ancient forests to compose their symphonies in shades of green alone. The absence of flowering plants creates ecological patterns unlike anything in the modern world. Without grasses to bind soil and create meadows, without deciduous trees to create seasonal leaf litter, without the explosive diversity of angiosperm families that dominate contemporary floras, these Jurassic landscapes operate according to different rules. The understory remains relatively open beneath the coniferous canopy, carpeted with ferns whose fronds catch the dappled sunlight filtering through branches that never knew the evolutionary pressure of competition with flowers. Araucaria trees, relatives of the modern monkey puzzle tree and Norfolk Island pine, dominate many Jurassic forest ecosystems with their distinctive umbrella-shaped crowns and spiral arrangements of leaves. These conifers grow to enormous sizes, some specimens reaching heights exceeding 60 meters with trunk diameters that rival the giant sequoias of today. The Petrified Forest of Arizona preserves the fossilized remains of these ancient giants, their silicified wood revealing growth rings that document seasonal variations in an otherwise greenhouse climate. The canopy architecture of these forests differs fundamentally from modern woodland systems. Without broad-leaved deciduous trees to create dense, light-blocking upper stories, Jurassic forests maintain relatively open canopies that allow substantial amounts of sunlight to penetrate to lower levels. This creates multi-story forest systems where different groups of plants occupy distinct vertical zones, tall conifers forming the emergent layer, smaller conifers and cycads creating a middle canopy, and ferns carpeting the forest floor. Cycads reach their evolutionary zenith during the Jurassic, earning this period the nickname Age of Cycads from early paleobotanists. These seed plants, which superficially resemble palms but represent an entirely separate evolutionary lineage, develop extraordinary diversity in both size and form. Some species grow as small understory plants with delicate compound leaves, while others achieve tree-like proportions with massive trunks and crowns of leaves that can reach lengths of several meters. Cycadioidea and Williamsonia represent some of the most common cycads in Jurassic floras, their fossilized trunks preserved in such detail that paleobotanists can study their internal anatomy and growth patterns. The reproductive strategies of these ancient plants reveal sophisticated adaptations that predate the evolutionary innovations of flowering plants. Many Jurassic conifers develop elaborate cone structures that protect their seeds during development and facilitate wind dispersal upon maturity. Some species produce resinous secretions that preserve insects and other small organisms, creating the amber deposits that will eventually provide extraordinary windows into Jurassic terrestrial ecosystems. The famous Burmese amber, though technically Cretaceous in age, preserves organisms whose lineages originated in these Jurassic forests. Ferns achieve remarkable diversity in the understory of these ancient woodlands, developing specialized forms for virtually every available terrestrial niche. Tree ferns create their own canopy layer in some environments, their trunks constructed from densely packed roots and leaf bases rather than true woody tissue. Osmunda. Cladophlebis and other fern genera develop specialized reproductive structures and spore dispersal mechanisms that allow them to compete effectively with seed plants for space and resources in the forest understory. The absence of grasses creates terrestrial ecosystems with fundamentally different nutrient cycling patterns than those that will characterize post-Cretaceous landscapes. Without the dense root systems and rapid turnover rates of grass communities, Jurassic soils develop different chemical and physical properties. Paleosol studies reveal that many Jurassic forest soils were highly weathered and nutrient-poor, suggesting that plant communities had evolved efficient mechanisms for conserving and recycling essential elements. Insect diversity explodes within these forest ecosystems, though the groups present differ significantly from modern insect faunas. Beetles begin their remarkable radiation during the Jurassic, developing the diverse feeding strategies and ecological roles that will make them the most species-rich group of animals on Earth. Early representatives of modern beetle families appear in the fossil record, including wood borers, predators, and even some primitive forms that may have fed on cycad and conifer seeds. The relationship between insects and plants during this period remains largely one of antagonism rather than the mutualistic partnerships that will characterize angiosperm insect coevolution. Most plant-insect interactions involve herbivory, with insects feeding on leaves, boring into stems, or consuming seeds and pollen. The fossil record preserves abundant evidence of insect damage on Jurassic plant fossils, including distinctive feeding traces that can often be attributed to specific insect groups. Dinosaurs move through these ancient forests with remarkable grace and diversity, their ecological roles reflecting the unique plant communities they inhabited. Sauropods like Camarasaurus and Brachiosaurus use their enormous size and long necks to browse on the high canopies of conifer trees. Their feeding strategies adapted to exploit resources unavailable to smaller herbivores. The wear patterns on sauropod teeth suggest these giants were capable of processing the tough, fibrous foliage of conifers and cycads with remarkable efficiency. Stegosaurs occupy the middle browsing zone, their distinctive backplates and tail spikes making them among the most recognizable dinosaurs of the Jurassic. These heavily built herbivores show dental adaptations for processing the relatively tough plant material available in pre-angiosperm ecosystems, with small teeth arranged in dental batteries that could efficiently crop and slice fibrous vegetation. The famous Stegosaurus of the Morrison Formation represents the pinnacle of stegosaur evolution, perfectly adapted to life in the coniferous woodlands of late Jurassic North America. Theropod dinosaurs adapt to the forest environments as both large predators and small opportunistic hunters. Allosaurus patrols the forest clearings and edges as an apex predator, while smaller theropods like Compsognathus pursue insects, small vertebrates, and possibly even early mammals through the understory vegetation. The diversity of theropod body sizes and feeding strategies reflects the complex three-dimensional structure of these forest ecosystems. Mystery pervades many aspects of these ancient forest communities, particularly the mechanisms that maintain plant diversity in the absence of the pollination mutualisms that drive much of modern angiosperm diversity. Recent studies of Jurassic plant reproductive structures suggest that some species may have developed primitive relationships with insects for pollen transfer, foreshadowing the co-evolutionary partnerships that will become so important in later periods. The preservation of these forest ecosystems varies dramatically depending on depositional environment and post-burial conditions. The most spectacular preservation occurs in environments where rapid burial by volcanic ash or flood sediments creates three-dimensional fossil forests with trees preserved in their growth positions. These fossil forests provide insights into canopy structure, tree spacing, and understory composition that cannot be obtained from isolated plant fossils. Paleoclimatic reconstructions based on Jurassic plant fossils reveal details of ancient atmospheric composition and seasonal patterns. The presence of fossil wood with well-developed growth rings in some regions suggests seasonal temperature or precipitation variations even within the overall greenhouse climate. Stomatal counts on fossil leaves provide estimates of atmospheric carbon dioxide concentrations that help calibrate climate models of ancient greenhouse periods. The chemical composition of Jurassic plant fossils preserves information about ancient plant physiology and biochemistry. Some specimens retain organic compounds that document the evolutionary history of plant secondary metabolites, the chemicals that plants use for defense against herbivores and pathogens. These molecular fossils suggest that many defensive compounds evolved long before the appearance of flowering plants, challenging assumptions about the timing of plant-herbivore evolutionary arms races. Geographic patterns of plant distribution during the Jurassic reflect both climatic influences and the continued fragmentation of Pangea. Endemic plant communities develop on the isolated landmasses created by rising sea levels, while some cosmopolitan species maintain broad distributions across the remaining continental connections. These biogeographic patterns provide insights into ancient climate gradients and continental positions that complement evidence from other geological sources. The legacy of these flowerless forests extends far beyond their immediate geological time period. Many of the ecological roles and adaptive strategies developed by Jurassic plants will be inherited by later angiosperm communities, while the insect groups that diversified in these ancient woodlands provide the foundation for the explosive coevolution between insects and flowering plants that will characterize the Cretaceous and Cenozoic eras. As these primeval forests reach their full development during the Middle and Late Jurassic, they create some of the most productive and complex terrestrial ecosystems in Earth's pre-angiosperm history. The cathedral-like spaces beneath their canopies echo with the footsteps of giants and the buzz of ancient insects, while their green architecture builds the foundation for evolutionary innovations that remain millions of years in the future. Only took the absence of flowers to create forests where every leaf was different, every branch a unique solution to the ancient problems of capturing light and surviving seasons in a world that bloomed only in shades of green. The giants walk on tiptoe. It is the late Jurassic, approximately 150 million years ago, and the earth trembles beneath the footsteps of the largest land animals that have ever lived. Yet, for all their immense bulk, Brachiosaurus reaching lengths of 26 meters and weights approaching 80 tons, these sauropod dinosaurs move through their forest world with surprising delicacy. Their massive feet, equipped with soft pads that distribute their weight across the yielding ground like enormous biological snowshoes. The physics of gigantism creates challenges that these ancient titans solve with engineering solutions both elegant and unexpected. A brachiosaurus standing at full height reaches 15 meters into the canopy, its head higher above the ground than a 4-story building. Yet the blood pressure required to pump blood to such heights would rupture the blood vessels of most vertebrates. Fossil evidence suggests sauropods evolved multiple hearts or auxiliary pumping mechanisms distributed along their necks, creating circulatory systems more complex than those of any living animal. The famous Morrison Formation of the western United States preserves one of the most complete records of these late Jurassic giants. Their fossilized bones scattered across ancient river channels and floodplains that once supported some of the most diverse dinosaur communities in Earth's history. Diplodocus, with its whip-like tail and impossibly long neck, shares these ancient landscapes with the heavily built Camarasaurus and the towering Brachiosaurus, each species occupying different feeding niches within the same forest ecosystems. Trackway evidence reveals details of sauropod behavior and locomotion that skeletal remains alone cannot provide. The Purgatoire River site in Colorado preserves hundreds of sauropod footprints that document herd behavior, with adults and juveniles of different sizes traveling together along ancient shorelines. The trackways show that these giants typically walked at speeds of 4 to 6 kilometers per hour, a pace that seems almost leisurely until one considers that each stride covers 4 to 5 meters of ground. The feeding strategies of these colossal herbivores reflect both their enormous energy requirements and the limitations of pre-angiosperm plant communities. A single Brachiosaurus likely consumed several tons of vegetation daily, stripping entire trees of their foliage with the efficiency of a living construction crane. The wear patterns on sauropod teeth suggest these animals were not particularly selective feeders. They processed whatever plant material their necks could reach, from tender conifer shoots to tough cycad fronds to fibrous fern stems. Different sauropod species developed distinct feeding strategies that reduced competition within shared ecosystems. Diplodocus and its relatives evolved pencil-like teeth adapted for stripping leaves from branches, while Camarasaurus developed broad, spoon-shaped teeth better suited for processing tougher plant material. Brachiosaurus occupied the highest feeding zone with its elevated head posture, accessing canopy resources unavailable to its contemporaries. The result was a three-dimensional partitioning of forest resources that allowed multiple giant species to coexist in the same environments. The reproductive biology of sauropods remains one of paleontology's most fascinating mysteries, complicated by the sheer logistical challenges of mating and nesting for animals of such enormous size. Recent discoveries of sauropod nesting grounds in Argentina and elsewhere reveal that these giants laid relatively small eggs, typically no larger than a football, despite the massive size of the adult animals. This suggests that sauropod young underwent extraordinary growth rates, increasing their body mass by factors of thousands as they matured from hatchling to adult size. The nesting behavior documented at sites like Aucamahuevo shows that sauropods return to the same nesting grounds repeatedly over thousands of years, creating vast colonial nesting areas where hundreds or possibly thousands of eggs were laid in close proximity. The eggs were often arranged in linear patterns that may represent the walking paths of nesting females, each depositing a clutch of eggs at regular intervals as they moved across the nesting ground. Social behavior among sauropods appears to have been more complex than their reputation as dim-witted giants might suggest. Trackway evidence documents age-segregated herds where juveniles traveled separately from adults, possibly to avoid accidental trampling by their enormous parents. Some sites preserve evidence of mixed-age herds moving together, with smaller individuals protected in the center of the group, a formation strategy still used by modern elephants and other large herbivores. The cardiovascular challenges faced by these giants extend beyond simple blood pressure considerations. The extreme length of sauropod, necks up to 15 meters in some species, created circulation pathways that required sophisticated adaptations to prevent blood pooling and ensure adequate oxygen delivery to the brain. Some researchers propose that sauropods may have evolved specialized valve systems in their neck veins, similar to those found in modern giraffes, but scaled up to accommodate necks several times longer. The respiratory systems of sauropods show remarkable convergence with those of modern birds, featuring air sacs that extend into hollow spaces within the vertebrae and ribs. This pneumatization not only reduced the weight of the skeleton, crucial for animals of such enormous size, but also created highly efficient respiratory systems capable of supporting the high metabolic rates necessary for active lifestyles. The air sac system may have also provided additional cooling capacity for these massive animals living in greenhouse climatic conditions. Predation pressure on adult sauropods came primarily from large theropod dinosaurs like Allosaurus and Ceratosaurus. Though the enormous size of mature sauropods provided substantial protection against most predators, bite marks on sauropod bones suggest that predation was more common on juveniles and subadults, while adults may have been largely immune to attack except when injured or weakened by disease or old age. The defensive strategies employed by sauropods included both passive and active elements. Their sheer size served as the primary deterrent to most predators, while some species developed additional defensive features. Diplodocus and its relatives possessed whip-like tails that could generate supersonic crack sounds capable of deterring or even injuring potential predators. Computer models suggest these tail tips could achieve speeds exceeding 50 meters per second, faster than the crack of a bullwhip. Environmental adaptations of sauropods reflect their need to process enormous quantities of relatively low-quality plant food. Fossilized gastroliths. Stomach stones used to aid digestion found in association with sauropod skeletons suggest these animals employed mechanical grinding systems similar to those of modern birds. The gastroliths, often polished smooth by constant movement within the digestive system, helped break down tough plant fibers and increase the efficiency of nutrient extraction. The geographic distribution of sauropod species during the late Jurassic reflects both their remarkable dispersal abilities and the continued connection of continental landmasses despite ongoing fragmentation. Closely related species appear on different continents, suggesting these giants were capable of crossing significant water barriers or that land connections persisted longer than previously thought. The cosmopolitan distribution of some sauropod groups contrasts with the more restricted ranges of smaller dinosaurs, highlighting the advantages of gigantism for long-distance dispersal. Paleontological techniques continue to reveal new details about sauropod biology and behavior through increasingly sophisticated analytical methods. Bone histology. The microscopic study of fossil bone tissue provides insights into growth rates, metabolism, and lifespan that cannot be obtained from external bone morphology alone. These studies suggest that sauropods achieve their enormous size through sustained rapid growth over periods of decades rather than centuries, reaching sexual maturity while still growing toward their maximum adult size. The legacy of sauropod gigantism extends far beyond the Jurassic period, influencing ecosystem structure and evolutionary patterns throughout the Mesozoic era. The browsing pressure exerted by these giants shaped plant community composition and may have influenced the evolution of plant defensive strategies. The enormous amounts of organic matter processed and deposited by sauropod herds created nutrient hotspots that supported diverse communities of smaller organisms, from dung beetles to decomposer bacteria. As these gentle giants reach the pinnacle of their diversity and abundance during the late Jurassic, they create landscapes unlike any seen before or since in Earth's history. Their patient procession through ancient forests leaves footprints that will be preserved for millions of years, while their fossilized bones provide windows into the possibilities and constraints of vertebrate gigantism. Only took a few million years of abundant plant food and stable climate for evolution to discover that sometimes bigger really is better, even when bigger means walking on tiptoe to avoid disturbing the smaller world below. The greenhouse doors swing open. It is the early Cretaceous, approximately 120 million years ago, and Earth begins its transformation into the most extreme hothouse climate in the planet's recorded history. Atmospheric carbon dioxide concentrations climb to levels 4 to 6 times higher than modern values, creating a greenhouse effect so intense that ice becomes nearly extinct across the entire globe. Even the polar regions bask in subtropical warmth, their temperatures rarely dropping below what modern temperate zones experience during their mildest summers. The mechanisms driving this unprecedented warming operate on multiple geological fronts simultaneously. Massive volcanic activity associated with the formation of large igneous provinces releases enormous quantities of carbon dioxide into the atmosphere at rates that dwarf modern industrial emissions. The Ontong Java Plateau, the Kerguelen Plateau, and other submarine volcanic complexes pump greenhouse gases into the ocean atmosphere system for millions of years, their cumulative effects overwhelming the planet's natural carbon sinks. Ocean temperatures rise to levels that challenge the survival limits of marine life. Sea surface temperatures in tropical regions reach values approaching 40 degrees Celsius, comparable to the hottest modern hot springs. Even more remarkably, deep ocean temperatures climb to 15-20 degrees Celsius, eliminating the thermal stratification that characterizes modern ocean systems. The result is a global ocean system with minimal temperature gradients from surface to sea floor and from equator to poles. The absence of polar ice caps creates feedback loops that amplify the warming trend. Without ice sheets to reflect incoming solar radiation, the polar regions absorb heat with unprecedented efficiency. Dark ocean water and ice-free land surfaces replace the highly reflective ice sheets, creating a positive feedback loop that drives temperatures ever higher. The ice albedo feedback, operating in reverse, helps maintain the greenhouse conditions for tens of millions of years. Sea levels respond to the thermal expansion and ice-free conditions by rising to heights not seen since the late Precambrian. Estimates suggest that Cretaceous sea levels stood 100 to 200 meters higher than today, submerging vast areas of the continent beneath warm, shallow seas. The Western Interior Seaway divides North America from the Gulf of Mexico to the Arctic Ocean, while similar epicontinental seas flood Europe, Asia, and other continental regions. The atmospheric composition during this greenhouse maximum differs dramatically from modern conditions. Water vapor concentrations increase exponentially with temperature, creating atmospheric moisture levels that support vast cloud systems and intense precipitation cycles. Yet, paradoxically, many continental interiors experience severe aridity as the enhanced greenhouse effect creates extreme temperature gradients between land and sea that disrupt normal precipitation patterns. Ocean circulation patterns adapt to the radically different thermal regime through the development of circulation systems unlike anything in the modern world. Without cold, dense polar water to drive thermohaline circulation, ocean currents depend primarily on wind patterns and the Earth's rotation to generate global circulation. The result is a sluggish, stratified ocean system where surface waters mix poorly with deeper layers, creating widespread oxygen depletion at intermediate depths. The marine carbon cycle undergoes fundamental reorganization as organic productivity responds to the changed oceanic conditions. Enhanced continental weathering rates, driven by the extreme temperatures and intense precipitation, deliver enormous quantities of nutrients to the ocean system. Combined with the elevated atmospheric carbon dioxide levels, these nutrients fuel marine productivity to levels that create some of the most extensive organic-rich sediment deposits in Earth's history. Black shale formations deposited during Cretaceous greenhouse intervals preserve evidence of oceanic conditions that seem almost alien compared to modern seas. These organic-rich sediments, formed under oxygen-depleted conditions, contain up to 20% organic carbon by weight values that indicate marine productivity and preservation rates far exceeding those of any modern ocean environment. The Cretaceous black shales of the Atlantic Ocean, the Pangea shale of North America, and similar formations worldwide document widespread oceanic anoxia during peak greenhouse conditions. Atmospheric oxygen concentrations fluctuate dramatically during this period, reflecting the complex interplay between enhanced organic matter burial and increased weathering rates. Some evidence suggests oxygen levels may have dropped to as low as 15% during certain intervals values that would make breathing difficult for modern humans and contribute to the unique physiological adaptations seen in Cretaceous organisms. The terrestrial realm responds to the greenhouse conditions through explosive plant diversification and the development of forest ecosystems of unprecedented complexity. Flowering plants begin their remarkable radiation during this period, though the early Cretaceous floras remain dominated by conifers and other gymnosperms. The combination of elevated carbon dioxide levels, warm temperatures, and abundant moisture creates ideal conditions for plant growth across vast areas of the globe. Continental positions during the early Cretaceous contribute to the extreme nature of the greenhouse climate through the configuration of ocean basins and atmospheric circulation patterns. The continued opening of the Atlantic Ocean creates new patterns of oceanic heat transport, while the position of continents allows for the development of vast epicontinental seas that act as heat reservoirs and moisture sources. Dinosaur communities flourish under these hothouse conditions, achieving diversity levels that rival or exceed those of any other period in their evolutionary history. The warm, equable climate allows dinosaurs to colonize polar regions for the first time, creating truly global distributions for many groups. Fossil evidence from Alaska, Antarctica, and other high-latitude locations documents diverse dinosaur faunas thriving in regions that today are too cold to support reptilian life. The plant-animal interactions that developed during this greenhouse interval lay the groundwork for the explosive coevolution between flowering plants and insects that will characterize the later Cretaceous and Cenozoic eras. Early angiosperm flowers, though still relatively simple compared to their later descendants, begin to attract insect pollinators through the production of nectar and distinctive visual and chemical signals. Mystery surrounds many aspects of how ecosystems functioned under such extreme climatic conditions. Modern organisms have few analogues for the physiological challenges faced by Cretaceous life forms, particularly the problems of thermoregulation and water balance in environments where temperatures routinely exceeded the thermal tolerance limits of most modern species. Paleoclimatic modeling of Cretaceous greenhouse conditions reveals the complex feedback systems that maintained such extreme warmth for tens of millions of years. Cloud formation patterns, precipitation cycles, and atmospheric circulation all operated according to different rules than those governing modern climate systems. The models suggest that once established, greenhouse conditions became self-reinforcing through various positive feedback mechanisms. Geochemical evidence from Cretaceous rocks preserves detailed records of atmospheric and oceanic composition during the greenhouse maximum. Carbon isotope ratios document the massive carbon cycle perturbations associated with volcanic outgassing and enhanced organic matter burial. Oxygen isotope signatures confirm the warm, equable conditions suggested by biological evidence while revealing details of seasonal and latitudinal temperature patterns. The early Cretaceous greenhouse represents one of Earth's great natural experiments in extreme climate conditions, providing insights into how planetary systems respond to massive carbon dioxide emissions and thermal forcing. The geological record of this period offers both warnings about the potential consequences of anthropogenic climate change and examples of life's remarkable ability to adapt to extreme environmental conditions. As atmospheric carbon dioxide concentrations reach their Cretaceous peak, the planet enters a climatic regime that has few parallels in Earth's history. The greenhouse doors have swung fully open, admitting levels of warmth and atmospheric moisture that will transform every ecosystem on the planet. The stage is set for evolutionary innovations that will reshape terrestrial and marine communities in ways that echo through the remainder of Earth's biological history. Only took a few million years of volcanic outgassing to turn the planet into a global sauna where palm trees grow at the poles and the ocean floors stay as warm as modern tropical seas. The first flowers bloom in silence. It is the mid-Cretaceous, approximately 100 million years ago, and the most revolutionary innovation in plant evolution unfolds without fanfare across the warming landscapes of Earth. Small, inconspicuous blossoms appear among the established communities of conifers and ferns, their petals and stamens representing solutions to reproductive challenges that will ultimately transform every terrestrial ecosystem on the planet. The angiosperms have arrived, and with them comes a cascade of evolutionary changes that will reshape the biological world more profoundly than any event since the origin of complex life itself. The earliest flowers bear little resemblance to the spectacular blooms that will characterize later angiosperm evolution. Archifructus, preserved in the fossil lake beds of northeastern China, produces tiny, simple flowers, lacking both petals and sepal structures so basic they might be overlooked as reproductive organs at all. Yet within these modest beginnings lies the genetic and developmental machinery that will generate the extraordinary floral diversity of modern plant communities. The evolutionary advantages of the angiosperm reproductive system become apparent through their rapid expansion across diverse habitats during the mid-Cretaceous. The enclosed ovary that gives flowering plants their scientific name, angiosperm, means enclosed seed, provides protection for developing embryos while allowing for more sophisticated mechanisms of pollination and seed dispersal. Unlike the naked seeds of gymnosperms, angiosperm seeds develop within specialized structures that can evolve intricate relationships with animal dispersers. Double fertilization represents one of the key innovations that drives angiosperm success. This unique reproductive process, found nowhere else in the plant kingdom, creates both a diploid embryo and a triploid endosperm tissue that serves as a nutrient source for the developing seedling. The endosperm provides a competitive advantage by allowing angiosperm seedlings to establish themselves more rapidly than gymnosperm competitors, particularly in disturbed or resource-poor environments. The diversification of angiosperm families during the Cretaceous occurs with unprecedented speed in evolutionary terms. Within 20 million years of their first appearance, flowering plants expand from a few primitive lineages to encompass most of the major groups that dominate modern floras: magnolids, monocots, and eudicots. The three main branches of angiosperm evolution diverge during this interval, each exploring different solutions to the challenges of terrestrial plant life. Pollination relationships between early flowering plants and insects create some of the first documented examples of coevolution in the fossil record. Beetles appear to be among the earliest angiosperm pollinators. Their fossil remains frequently found in association with primitive flowers. These early pollination relationships lack the sophisticated specificity that will characterize later plant-pollinator interactions, with most early flowers producing generalized attractants that appeal to diverse insect visitors. The development of specialized floral structures proceeds through a series of evolutionary experiments that test different approaches to attracting pollinators and ensuring reproductive success. Early flowers experiment with various combinations of petals, sepals, stamens, and carpels, creating a diversity of floral architectures that will eventually be refined into the specialized pollination systems of modern flowering plants. Leaf architecture undergoes dramatic changes as angiosperms develop new approaches to photosynthesis and water transport. The evolution of complex venation patterns allows angiosperm leaves to achieve higher rates of photosynthesis and transpiration than their gymnosperm counterparts. Broad, flat leaves with intricate vascular networks become increasingly common in angiosperm lineages, providing superior light capture and gas exchange capabilities. The chemical warfare between plants and herbivores intensifies dramatically with the angiosperm radiation. Flowering plants develop an unprecedented array of secondary metabolites, alkaloids, terpenoids, phenolic compounds, and other defensive chemicals that deter herbivorous insects and other plant consumers. This biochemical arms race drives much of the diversification seen in both plant and insect lineages during the Cretaceous period. Fruit evolution represents another major innovation that contributes to angiosperm success. Unlike gymnosperm seeds, which rely primarily on wind dispersal, angiosperm fruits evolve intricate relationships with animal dispersers. Early fruits include simple structures like follicles and capsules, but the lineage quickly experiments with fleshy fruits that attract vertebrate dispersers through nutritional rewards. The ecological impact of the angiosperm radiation extends far beyond the plants themselves, fundamentally altering the structure and function of terrestrial ecosystems. The rapid growth rates and efficient resource utilization of many flowering plants allow them to colonize disturbed habitats and quickly establish dominance over slower-growing gymnosperm competitors. This competitive advantage becomes particularly pronounced in environments subject to frequent disturbance, such as riverbanks, forest gaps, and areas affected by volcanic activity. Insect diversity explodes in response to the new ecological opportunities created by flowering plants. The evolution of specialized feeding structures allows insects to exploit the nectar, pollen, and other resources provided by flowers, while the development of plant-specific feeding relationships drives the evolution of numerous specialist herbivore lineages. The total number of insect species increases by several orders of magnitude during the angiosperm radiation, creating the foundation for the extraordinary arthropod diversity that characterizes modern terrestrial ecosystems. The rise of flowering plants coincides with significant changes in vertebrate communities as well. The increased productivity and seasonal resource availability created by angiosperm communities support more diverse assemblages of herbivorous dinosaurs, while the proliferation of fruit and seed resources creates new feeding opportunities for smaller vertebrates, including early mammals and birds. Paleobotanical evidence from mid-Cretaceous deposits reveals the remarkable speed with which angiosperms colonize diverse habitats across the globe. Within just a few million years of their first appearance, flowering plants can be found in environments ranging from wetlands and riverbanks to upland forests and even some arid regions. This rapid geographic expansion reflects both their superior competitive abilities and their remarkable ecological flexibility. The fossil record preserves extraordinary details of early angiosperm evolution through sites like the Potomac Group of the eastern United States and the Crato Formation of Brazil. These deposits contain not only fossilized flowers, fruits, and leaves, but also preserved pollen grains that document the early stages of angiosperm reproductive biology. The microscopic details visible in these fossils reveal developmental patterns and cellular structures that provide insights into the genetic mechanisms underlying angiosperm innovation. Wood anatomy evolves rapidly in angiosperm lineages, with the development of vessel elements that provide more efficient water transport than the tracheids found in gymnosperm wood. These anatomical innovations allow flowering plants to achieve higher rates of photosynthesis and growth, particularly in warm, moist environments where rapid water transport becomes a limiting factor for plant productivity. The chemical composition of angiosperm tissues differs significantly from that of gymnosperms, with implications for both herbivore nutrition and decomposer ecology. Many flowering plants produce tissues with higher nitrogen content and fewer defensive compounds than gymnosperm foliage, making them more palatable to herbivores but also more rapidly decomposed after death. This creates nutrient cycling patterns that differ substantially from those in gymnosperm-dominated ecosystems. Mystery still surrounds many aspects of early angiosperm evolution, including the precise environmental conditions that favored their initial radiation and the genetic mechanisms that allowed such rapid morphological diversification. Recent molecular studies suggest that the genetic toolkit for flower development evolved through the duplication and modification of developmental regulatory genes, but the fossil record provides limited insights into these early evolutionary processes. The geographic origins of angiosperms remain contentious, with fossil evidence pointing to multiple centers of early diversification rather than a single point of origin. This pattern suggests that the fundamental innovations underlying flowering plant success evolved independently in different lineages, or that early angiosperms dispersed very rapidly from their initial area of origin. As the mid-Cretaceous greenhouse climate provides ideal conditions for plant growth and diversification, the angiosperm radiation accelerates into one of the most spectacular evolutionary events in Earth's history. The modest flowers that first appear in fossil deposits of this age represent the beginning of a transformation that will ultimately produce the estimated 300,000 species of flowering plants that dominate modern terrestrial ecosystems. The silence of these first blooms belies their revolutionary significance. Within the petals and stamens of Cretaceous flowers lies the blueprint for ecological relationships of stunning complexity and beauty pollination mutualisms, fruit dispersal partnerships, and chemical defenses that will shape the evolution of terrestrial life for the remainder of Earth's history. Only took a few inconspicuous flowers to begin the greatest diversification of terrestrial life since the Cambrian explosion, proving that sometimes the quietest revolutions echo the longest through deep time. The seas turn white with microscopic snow. It is the mid-Cretaceous, approximately 95 million years ago, and Earth's oceans undergo one of the most spectacular transformations in marine history. Countless billions of coccolithophores, single-celled marine algae, no larger than the period at the end of this sentence, bloom in such extraordinary numbers that they turn entire ocean basins into milky white seas. Each tiny organism constructs elaborate calcium carbonate plates called coccoliths, and when these microscopic architects die, their skeletal remains drift downward through the water column like an eternal blizzard of limestone snow. The scale of coccolithophore productivity during the Cretaceous greenhouse period defies modern comprehension. Individual blooms extend across ocean basins, visible from space as vast white patches that persist for months or even years. The white cliffs of Dover, the chalk deposits of Kansas, the limestone formations of the Paris Basin all represent the accumulated remains of these ancient marine snowstorms. Their white stone, composed almost entirely of coccoliths, deposited grain by microscopic grain across millions of years. The evolutionary innovations that drive this remarkable expansion begin with the perfection of cellular biomineralization. Coccolithophores develop sophisticated intracellular machinery for precipitating calcium carbonate in precise geometric patterns that vary by species. Each coccolith represents a masterpiece of biological engineering, with plates, spines, and other ornamental features constructed according to species-specific blueprints encoded in the organism's DNA. The geometric complexity rivals that of diatoms, yet these structures form from calcium carbonate rather than silica, making them readily preserved in the fossil record. The ecological success of coccolithophores reflects their dual nature as both photosynthetic organisms and calcifying machines. Like other phytoplankton, they harness sunlight to convert carbon dioxide and water into organic compounds through photosynthesis. However, their calcification process actually releases carbon dioxide back into seawater, creating a complex relationship with the ocean carbon cycle that influences both local water chemistry and global atmospheric composition. The warm, carbon dioxide-rich Cretaceous oceans provide ideal conditions for coccolithophore proliferation. High atmospheric CO2 levels ensure abundant dissolved carbon dioxide in seawater, while the elevated temperatures accelerate both photosynthesis and calcification rates. The absence of polar ice caps creates warm, stratified oceans with extensive areas of nutrient-rich surface water, where these organisms can flourish without competition from cold water phytoplankton groups. Ocean chemistry during the Cretaceous differs dramatically from modern conditions in ways that favor calcium carbonate precipitation. Higher concentrations of dissolved calcium and carbonate ions, combined with elevated temperatures, create supersaturated conditions that make calcification easier for marine organisms. The ocean pH remains slightly higher than modern values despite elevated atmospheric CO2, reflecting the complex buffering effects of enhanced weathering rates on land. The diversity of coccolithophore species reaches unprecedented levels during the mid-Cretaceous, with dozens of genera and hundreds of species coexisting in the same water masses. Each species produces distinctive coccolith morphologies that allow paleontologists to identify them in rock samples and reconstruct ancient ocean conditions. Watsnaueria, Prediscosphaera, Eiphilithus, and other genera develop elaborate coccolith architectures that serve both protective and possibly competitive functions. The massive scale of coccolithophore blooms creates positive feedback loops that enhance their own success. The white calcium carbonate particles increase the reflectivity of ocean surface waters, potentially influencing local climate patterns and creating conditions that favor continued blooming. Additionally, the alkalinity changes caused by mass calcification may alter seawater chemistry in ways that promote further coccolith formation. The ecological interactions between coccolithophores and other marine organisms during the Cretaceous remain partially mysterious. These tiny algae serve as the base of marine food webs, supporting diverse communities of zooplankton, fish, and other organisms. Yet, their calcium carbonate armor may provide protection against some types of predation, allowing them to achieve population densities that would be impossible for unarmored phytoplankton. The sedimentation rates in areas of intense coccolithophore productivity reach extraordinary levels during Cretaceous greenhouse intervals. The Niobrara Formation of the central United States, accumulated at rates exceeding 10 centimeters per thousand years, values that reflect the incredible productivity of the overlying surface waters. Individual limestone beds within these formations can be traced across hundreds of kilometers, documenting the regional extent of ancient blooming events. Marine reptiles navigate through these chalky seas as apex predators, their fossilized remains occasionally preserved within the coccolith-rich sediments. Hesperornis, a toothed diving bird reaching lengths of nearly 2 meters, pursues fish through waters that appear more like liquid milk than the clear blue oceans familiar to modern eyes. The preservation of soft tissues in some specimens suggests that the alkaline conditions created by mass coccolith deposition may have enhanced fossilization potential. The trace element chemistry of coccoliths preserves detailed records of ancient seawater composition and temperature. Magnesium to calcium ratios in coccolith calcite reflect seawater temperature, while strontium isotope signatures document the balance between continental weathering and hydrothermal input from oceanic ridge systems. These chemical archives provide some of the most detailed paleoceanographic records available from the Mesozoic era. Different coccolithophore species show distinct ecological preferences that create depth-stratified communities within the water column. Some species prefer the highlight conditions near the surface, while others thrive in the deeper euphotic zone where light levels are reduced, but nutrient concentrations may be higher. This vertical partitioning allows multiple species to coexist without direct competition, contributing to the extraordinary diversity seen in Cretaceous assemblages. The seasonal cycles of coccolithophore productivity create rhythmic patterns in the sedimentary record that document ancient climate variability. Laminated limestone formations preserve annual couplets of coccolith-rich and coccolith-poor layers that may reflect seasonal blooming cycles controlled by temperature, nutrient availability, or other environmental factors. These rhythmites provide insights into the periodicity of ancient climate systems at timescales ranging from annual to millennial. The global distribution of coccolithophore species during the Cretaceous reflects both their dispersal capabilities and the environmental gradients that existed even within the greenhouse climate regime. Some species achieve cosmopolitan distributions across all ocean basins, while others show more restricted geographic ranges that may reflect adaptation to specific temperature, salinity, or nutrient conditions. The biomineralization process itself represents one of the most sophisticated examples of biological control over inorganic crystal formation. Coccolithophores construct their calcium carbonate plates within specialized intracellular compartments called coccolith vesicles, where they can precisely control the chemical conditions necessary for crystal nucleation and growth. The resulting coccoliths often display crystallographic properties that differ from inorganic calcite, reflecting the biological control exerted during formation. The evolutionary relationships among Cretaceous coccolithophores reveal rapid diversification and morphological experimentation during the greenhouse maximum. New species appear and disappear from the fossil record at rates that suggest accelerated evolutionary turnover, possibly driven by the environmental instability associated with oceanic anoxic events and other climate perturbations. The mass extinction events that punctuate Cretaceous history have variable effects on coccolithophore communities, with some groups showing remarkable resilience while others suffer severe diversity losses. The differential survival of species during these crises provides insights into the environmental factors that control coccolithophore evolution and may help predict their responses to future climate change. As the Cretaceous greenhouse reaches its thermal maximum, coccolithophore productivity creates ocean conditions unlike any seen before or since in Earth's history. The white seas they produce represent a unique phase in marine evolution, when tiny single-celled organisms achieved such abundance that they fundamentally altered the optical properties of entire ocean basins. The legacy of these ancient blooms extends far beyond their immediate geological time period. The limestone formations they created serve as aquifers, building stones, and repositories of paleoclimatic information for hundreds of millions of years. Their fossil remains provide windows into ocean chemistry and climate dynamics during one of Earth's most extreme greenhouse periods, while their modern descendants continue to play crucial roles in marine ecosystems and global biogeochemical cycles. The microscopic snow falls endlessly through Cretaceous seas. Each tiny coccolith a testament to the power of biology to reshape planetary systems through the accumulation of countless small acts. Only took organisms smaller than dust particles to paint the oceans white and create stone monuments that will endure until the continents themselves are worn to sand by the patient work of wind and rain. The forests grow in darkness and light. It is the late Cretaceous, approximately 85 million years ago, and dense woodlands carpet the polar regions of Earth in a botanical paradox that challenges every assumption about plant life at high latitudes. In what is now northern Alaska and the Antarctic Peninsula, vast forests of deciduous conifers thrive under climatic conditions that seem almost impossible: months of continuous summer daylight, followed by months of winter darkness, yet with temperatures that rarely drop below freezing even during the polar night. The trees that dominate these polar forests belong to families that still exist today, yet their ancestors live under environmental conditions that have no modern analog. Metasequoia. The dawn redwood forms extensive stands along the ancient coastlines, its feathery foliage creating cathedral-like spaces beneath canopies that may reach heights of 40 meters or more. These deciduous conifers have solved the puzzle of surviving polar winters not through cold tolerance, but through evolutionary strategies adapted to months of complete darkness. The seasonal rhythms of these polar forests operate according to astronomical rather than thermal cycles. During the brief polar summer, when the sun never sets, photosynthesis proceeds at extraordinary rates under the continuous illumination. The trees compress an entire growing season into just a few months of perpetual daylight, producing annual growth rings that reflect this intense but temporally compressed productivity. When autumn arrives with its rapidly shortening days, the conifers shed their needles in preparation for the long polar night. The winter dormancy period in these forests lasts for months of complete darkness, yet temperatures remain surprisingly mild due to the greenhouse effect of elevated atmospheric carbon dioxide levels. Snow may fall occasionally, but the ground rarely freezes, allowing soil organisms and root systems to remain active throughout the dark season. The forests essentially hibernate in a state of suspended animation, waiting for the return of sunlight to trigger the explosive growth of another polar summer. The plant communities of these polar forests display remarkable diversity despite the extreme photoperiod conditions. Ginkgo trees, tree ferns, and various angiosperms create a complex understory beneath the coniferous canopy. Broad-leaved deciduous trees, including early relatives of modern plane trees and magnolias, develop strategies for surviving the extended dark period through enhanced nutrient storage and modified dormancy physiology. Fossil leaf deposits from these polar forests preserve evidence of plant physiological adaptations that seem almost contradictory to their environmental context. Many species develop unusually large leaves with prominent venation patterns that maximize light capture during the brief growing season. The leaf margins often lack the teeth and lobing typical of plants adapted to cold climates, instead displaying the smooth edges characteristic of warm climate vegetation, a reflection of the mild temperatures that persist even during polar winters. The animal communities that inhabit these polar forests include dinosaurs whose presence at such high latitudes was long considered impossible. Triceratops and other ceratopsians browse through the undergrowth of Alaskan forests, while small theropods hunt among the tree ferns and cycads. These dinosaurs must possess physiological adaptations that allow them to function during the months-long polar night, possibly including enhanced metabolic efficiency or behavioral modifications such as migration or extended dormancy periods. The preservation of these polar forest ecosystems creates some of paleobotany's most spectacular fossil localities. The rapid burial of entire forest communities by volcanic ash or flood sediments preserves three-dimensional forest structures with trees in their growth positions. These fossil forests provide unprecedented insights into the architecture and ecology of plant communities adapted to extreme photoperiod conditions. The soil development in polar forests during the Cretaceous greenhouse period produces distinctive paleosol profiles that reflect the unique combination of warm temperatures and extreme seasonal light variation. Root traces, burrow systems, and chemical weathering patterns document the activity of soil organisms throughout the year, including the dark winter months when photosynthesis ceases, but soil biological processes continue at reduced rates. The hydrology of polar forest watersheds operates under conditions unlike those of any modern ecosystem. River systems flow throughout the year due to the mild temperatures, but their discharge patterns reflect the seasonal cycles of plant activity rather than temperature-driven freeze-thaw cycles. Peak flows occur during the polar summer when transpiration rates reach maximum levels, while winter flows remain relatively stable despite the absence of photosynthetic activity. Marine influences on these polar forests create coastal ecosystems where terrestrial and marine productivity intersect in unique ways. Fossil localities preserve evidence of coastal plain forests where dinosaurs and marine reptiles inhabited adjacent environments separated by just a few kilometers. The proximity of warm polar seas provides thermal buffering that further moderates the winter climate and may supply moisture for precipitation throughout the dark season. The biogeography of polar forest species reveals complex patterns of adaptation and migration that reflect both the extreme photoperiod conditions and the continued fragmentation of Pangea. Some plant groups appear to be endemic to polar regions, having evolved specialized adaptations for life at high latitudes, while others represent cosmopolitan species that achieved circumpolar distributions during periods of especially warm climate. The evolutionary innovations developed by polar forest plants include sophisticated photoperiod sensing mechanisms that allow them to anticipate seasonal changes in daylight hours. These biological clocks must be calibrated to respond to the gradual changes in day length that occur over periods of months, rather than the rapid daily light-dark cycles that characterize lower latitudes. The carbon cycling in polar forests during the Cretaceous greenhouse period operates under conditions that have no modern equivalent. The combination of high atmospheric CO2 concentrations, warm temperatures, and extreme photoperiod variations creates unique patterns of carbon fixation, storage, and release. Massive accumulations of organic matter during the brief growing seasons alternate with periods of slow decomposition during the dark winters. The reproductive strategies of polar forest plants must accommodate the constraints imposed by the extreme seasonal light cycles. Many species appear to concentrate their reproductive activities into the brief polar summer, when energy availability reaches peak levels. Pollen and seed production occur under conditions of continuous daylight, while seed germination and seedling establishment must be timed to take advantage of the favorable conditions that persist for only a few months each year. The mycorrhizal relationships between plant roots and soil fungi become particularly important in polar forest ecosystems, where the extended periods of darkness limit direct carbon fixation by plants. The fungal networks that connect tree root systems may serve as carbon storage and redistribution systems that help sustain plant communities through the long polar winters. The atmospheric chemistry above polar forests during the Cretaceous differs from that at lower latitudes due to the unique patterns of photosynthesis and respiration imposed by extreme photoperiod conditions. Oxygen and carbon dioxide concentrations fluctuate seasonally in response to the boom and bust cycles of biological activity, creating atmospheric compositions that vary dramatically between summer and winter. The paleoclimatic implications of polar forests extend far beyond their immediate geographic extent, providing crucial constraints on global climate models of the Cretaceous greenhouse period. The presence of diverse forest communities at latitudes where temperatures today remain below freezing year-round requires heat transport mechanisms and greenhouse gas concentrations that challenge our understanding of Earth's climate system. The modern descendants of Cretaceous polar forest plants provide living laboratories for understanding the physiological mechanisms that allowed their ancestors to thrive under such extreme conditions. Dawn redwoods, ginkgos, and other living fossils retain genetic and physiological characteristics that may reflect adaptations to the unique environments of ancient polar forests. As the late Cretaceous greenhouse reaches its climatic peak, polar forests represent one of the most remarkable adaptations to extreme environmental conditions in the history of terrestrial life. These dark adapted woodlands demonstrate the extraordinary flexibility of plant communities and the power of evolutionary innovation to colonize even the most challenging environments on Earth. The legacy of these polar forests lives on in the coal deposits and fossil localities that preserve their remains, providing windows into Earth's capacity for sustaining complex ecosystems under climatic conditions that seem almost alien compared to the modern world. Only took a few degrees of global warming to turn the polar regions into gardens where trees learn to sleep through months of darkness and wake to summers that never saw the night. The diversity explodes in silence. It is the late Cretaceous, approximately 75 million years ago, and Earth experiences the greatest expansion of complex life in its terrestrial history. Dinosaur species proliferate into ecological niches that seem to anticipate every possible way of being a large land animal, while flowering plants and their insect partners engage in co-evolutionary dances of stunning intricacy. The planet has become a biological laboratory where evolutionary experiments unfold on a scale that dwarfs the diversity of any previous or subsequent period. The dinosaur communities of this time achieve a taxonomic richness that challenges paleontologists' ability to classify and understand them. In the Badlands that will become Montana and Alberta, over 40 different dinosaur species coexist in single formations, their ecological roles partitioned with mathematical precision. Ceratopsians alone diversify into dozens of species, each distinguished by unique horn and frill arrangements that may serve functions ranging from species recognition to thermoregulation to predator deterrence. Triceratops, Torosaurus, Pentaceratops, and their relatives demonstrate how evolution explores every possible variation on the theme of the horned dinosaur body plan. Some species develop forward-curving horns optimized for combat, while others evolve elaborate frill decorations that create visual displays rivaling the peacock's tail in their complexity. The speed of this diversification suggests that ceratopsian evolution operates under intense selective pressures that drive morphological innovation at unprecedented rates. Hadrosaurs. The duck-billed dinosaurs achieve even greater diversity through their remarkable experiments with cranial acoustics and dental mechanics. Parasaurolophus develops hollow crests that function as resonating chambers, each species tuned to produce different frequencies and harmonics. These dinosaur orchestras may have filled late Cretaceous landscapes with complex vocalizations that served purposes ranging from mate attraction to territorial defense, to parent-offspring communication. The dental innovations of hadrosaurs represent some of the most sophisticated herbivorous adaptations in vertebrate history. Their dental batteries contain hundreds of individual teeth arranged in grinding surfaces that can process the toughest plant materials with remarkable efficiency. As flowering plants diversify and develop new defensive chemicals and structural adaptations, hadrosaur dentition evolves in parallel to overcome these plant defenses. Theropod dinosaurs explore nearly every conceivable predatory lifestyle during this period of maximum diversity. Tyrannosaurus rex represents the apex of large predator evolution. Its massive skull and bone-crushing teeth adapted for hunting the largest herbivorous dinosaurs. Yet, smaller theropods diversify into roles that anticipate many modern predatory strategies: pack hunters, fish specialists, insectivores, and even possible scavengers that clean up the remains left by larger predators. The evolutionary arms race between predators and prey reaches extraordinary levels of sophistication. Ankylosaurs develop body armor that transforms them into living tanks, their bony plates and tail clubs creating defensive systems that can withstand attacks from even the largest theropods. Therizinosaurus evolves claws over 1 meter in length. Though these fearsome weapons may serve primarily for gathering vegetation rather than combat, flight evolves independently multiple times during this period, creating aerial communities of stunning diversity. Pteranodon and other pterosaurs achieve wingspans exceeding 7 meters, soaring over Cretaceous seas as efficient as modern albatrosses. Birds diversify rapidly from their theropod ancestors, developing the flight capabilities and metabolic innovations that will eventually allow them to survive the end Cretaceous extinction while their dinosaurian relatives perish. The coevolutionary relationships between flowering plants and insects create feedback loops that drive diversification in both groups simultaneously. Early bees develop sophisticated pollen-collecting structures and social behaviors, while flowers evolve increasingly complex shapes, colors, and chemical attractants to ensure pollination services. Butterflies and moths radiate into hundreds of species, their larvae developing specialized feeding relationships with particular plant families. The chemical complexity of plant-insect interactions reaches levels that rival modern tropical ecosystems. Plants develop alkaloids, terpenes, and other secondary metabolites in an evolutionary arms race against herbivorous insects, while insects evolve detoxification mechanisms and specialized feeding behaviors that allow them to exploit these defended resources. Some insects even co-opt plant defensive chemicals for their own protection, creating multi-trophic level chemical webs that influence entire ecosystem dynamics. Flowering plant diversity explodes into forms that explore nearly every possible architectural solution to the challenges of terrestrial plant life. Early relatives of modern families, roses, legumes, magnolias, and others establish the morphological foundations for the angiosperm-dominated ecosystems that will characterize the Cenozoic era. Some lineages develop tree-like growth forms that compete directly with conifers for canopy space, while others explore understory niches or develop climbing strategies that use established trees as structural support. The fruit and seed dispersal mechanisms developed by late Cretaceous angiosperms demonstrate evolutionary innovation at its most creative. Some plants develop explosive seed pods that scatter their offspring across considerable distances, while others produce fleshy fruits that attract dinosaur dispersers. The coevolution between plants and their animal dispersers creates mutualistic relationships that benefit both partners while driving continued diversification in both groups. Mammal diversity, while still constrained by the dominance of dinosaurs, reaches new heights during the late Cretaceous. multituberculates, extinct mammals with sophisticated dental adaptations diversify into ecological niches ranging from seed specialists to possible gliders. Early placental mammals develop the reproductive innovations that will eventually allow them to outcompete other mammalian groups in post-extinction ecosystems. The marine realm experiences its own diversity explosion as oceanic ecosystems mature under greenhouse climatic conditions. Ammonoids achieve their final evolutionary flowering, with shell forms that explore every possible variation on the coiled cephalopod theme. Rudist bivalves create reef systems that rival modern coral reefs in their complexity and productivity, while marine reptiles diversify into forms adapted for every conceivable aquatic lifestyle. The preservation of late Cretaceous ecosystems in formations like the Hell Creek and Dinosaur Park formations creates fossil assemblages of extraordinary richness that document this peak of terrestrial diversity. These deposits preserve not only the skeletons of large dinosaurs, but also the remains of smaller organisms, insects, leaves, pollen grains, and other components of complete ecosystem communities. The biogeographic patterns established during this period reflect both the continued fragmentation of Pangea and the dispersal capabilities of different organism groups. Some dinosaur families achieve nearly cosmopolitan distributions, while others show high levels of endemism that document the evolution of isolated continental faunas. The balance between endemism and cosmopolitanism creates biogeographic complexity that rivals that of modern continental systems. The trophic structure of late Cretaceous ecosystems achieves levels of complexity that anticipate many aspects of modern ecological organization. Food webs include multiple levels of primary producers, herbivores, and carnivores, with energy flow pathways that create stable community structures capable of supporting extraordinary numbers of species. The ecological roles filled by different dinosaur species show niche partitioning patterns that minimize competition while maximizing resource utilization efficiency. Mystery still surrounds many aspects of how such high diversity was maintained in late Cretaceous ecosystems. Modern ecological theory suggests that high diversity requires environmental heterogeneity and disturbance regimes that prevent competitive exclusion. Yet many late Cretaceous formations appear to represent relatively stable environmental conditions. The answer may lie in the three-dimensional complexity of forest ecosystems and the temporal variability created by seasonal and longer-term climate cycles. The metabolic innovations that support this diversity explosion include physiological adaptations that allow large dinosaurs to maintain active lifestyles despite their enormous body sizes. Advanced respiratory systems, sophisticated thermoregulatory mechanisms, and efficient digestive systems all contribute to the ability of late Cretaceous dinosaurs to achieve both large body sizes and high species diversity within the same ecosystems. As the late Cretaceous approaches its climax, the biological diversity of Earth reaches levels that may not have been equaled before or since. The silence of this explosion reflects the gradual nature of evolutionary processes. Each new species, each co-evolutionary innovation, each ecological relationship developing over thousands of generations without fanfare or celebration. Yet, the cumulative effect creates a living world of breathtaking complexity and beauty, a planetary ecosystem operating at peak biological performance. The stage is set for one of the great transitions in Earth's history. As this pinnacle of Mesozoic diversity faces the approaching challenges that will reshape life on Earth. Only took 185 million years of reptilian experimentation to create a world where giants walked among flowers and the very air hummed with the wings of insects, exploring every conceivable way of being alive. The Earth bleeds basalt across a subcontinent. It is 66.5 million years ago, and the Deccan Traps of Western India begin their catastrophic eruption with a violence that dwarfs human comprehension. Lava flows stretch across landscapes for hundreds of kilometers, while volcanic gases pour into the atmosphere at rates that fundamentally alter global climate systems. This is not the familiar cone-shaped volcano of popular imagination, but rather flood basalt volcanism on a scale that occurs perhaps once every 100 million years, an event so massive that it rivals the asteroid impact as a driver of mass extinction. The eruptions unfold in episodic pulses that persist for nearly 1 million years, each phase adding new layers to a basaltic province that will eventually cover an area larger than modern France. Individual lava flows extend for distances that modern volcanic eruptions cannot approach, their leading edges advancing across the landscape at walking pace, while temperatures exceeding 200 degrees Celsius incinerate everything in their path. The cumulative volume of erupted material exceeds 1 million cubic kilometers, enough basalt to bury the entire continental United States under several meters of volcanic rock. The atmospheric consequences of such massive volcanism begin with the release of sulfur dioxide in quantities that eclipse all other natural sources combined. These emissions react with water vapor in the stratosphere to form sulfuric acid aerosols that scatter incoming solar radiation back to space, creating periods of volcanic winter that can persist for years following major eruptive phases. Global temperatures drop by several degrees during the most intense volcanic intervals, disrupting ecosystems already stressed by the longer-term warming effects of carbon dioxide emissions. Carbon dioxide release from the Deccan eruptions occurs at rates that overwhelm the natural carbon sinks that normally regulate atmospheric greenhouse gas concentrations. Each cubic kilometer of erupted basalt releases approximately 100 million tons of CO2, creating cumulative emissions that drive atmospheric concentrations to levels not seen since the early Triassic. The resulting greenhouse effect interacts with the cooling effects of volcanic aerosols to create climate instability of unprecedented magnitude. The marine realm suffers particularly severe disruption as oceanic chemistry responds to the massive influx of volcanic gases. Ocean acidification accelerates as carbon dioxide dissolves into seawater, while the input of mercury, lead, and other toxic heavy metals from volcanic emissions creates poisonous conditions throughout marine food webs. The shallow epicontinental seas that had supported such rich marine ecosystems during the Cretaceous greenhouse period become killing fields where even the most successful marine groups face extinction. Atmospheric mercury concentrations spike to levels that exceed the tolerance limits of most vertebrate species. This heavy metal bioaccumulates in food webs, reaching toxic concentrations in top predators that depend on long food chains for their energy supply. The mercury signature preserved in latest Cretaceous rocks provides one of the clearest chemical fingerprints of the Deccan volcanism and its biological effects. The timeline of Deccan volcanism reveals a complex pattern of eruptive phases that may have interacted synergistically with other environmental stresses to drive ecosystem collapse. Some of the most voluminous eruptive phases occur in the hundreds of thousands of years immediately preceding the end Cretaceous boundary, suggesting that volcanic stress may have weakened ecosystems and made them more vulnerable to the final catastrophe that will end the Mesozoic era. Dinosaur communities show signs of stress and declining diversity during the final stages of the Cretaceous, with some groups disappearing from the fossil record well before the boundary itself. Whether this reflects sampling bias, gradual environmental deterioration, or the direct effects of Deccan volcanism remains one of paleontology's most contentious debates. The fossil record suggests that some dinosaur groups maintained high diversity until the very end of the Cretaceous, while others show evidence of decline beginning hundreds of thousands of years earlier. Plant communities respond to the volcanic stress through shifts in species composition that favor taxa adapted to disturbed environments and variable atmospheric conditions. Fern spores become increasingly abundant in latest Cretaceous sediments, suggesting the expansion of pioneer plant communities that colonize landscapes devastated by acid rain and volcanic ashfalls. The intricate coevolutionary relationships between flowering plants and insects begin to unravel as environmental stress overwhelms the mutualistic partnerships that had driven late Cretaceous diversification. The geographic extent of Deccan volcanism influences global climate patterns through mechanisms that extend far beyond the immediate volcanic province. Ash clouds and aerosol plumes circle the globe multiple times before settling out of the atmosphere, creating worldwide atmospheric disturbances that affect precipitation patterns, seasonal temperature cycles, and atmospheric circulation systems. The Indian Ocean becomes a cauldron of volcanic activity as submarine eruptions add to the atmospheric burden of volcanic gases. Marine productivity crashes in many regions as oceanic food webs collapse under the combined stress of acidification, heavy metal poisoning, and disrupted nutrient cycling. The massive coccolithophore blooms that had characterized Cretaceous seas disappear from many areas, while planktonic foraminifera and other key marine groups show dramatic diversity losses. The marine extinction begins gradually, accelerating through the final million years of the Cretaceous as volcanic activity intensifies. Terrestrial ecosystems face their own cascade of environmental challenges as acid rain strips nutrients from soils and poisons freshwater systems. The chemical weathering rates of exposed rock surfaces accelerate under the acidic conditions, altering drainage patterns and creating widespread soil instability. Forest communities that had achieved extraordinary diversity during the late Cretaceous begin to fragment and collapse as their constituent species face physiological challenges beyond their adaptive capacity. The trace fossil record from latest Cretaceous sediments documents behavioral changes in surviving animal communities that suggest increasing environmental stress. Dinosaur trackways show alterations in gait and group structure that may reflect nutritional stress or behavioral responses to deteriorating environmental conditions. Burrow systems become more complex and deeper, possibly reflecting attempts by smaller organisms to escape the toxic surface conditions. Geochemical studies of Deccan lava flows reveal the complex magma chamber processes that drove such massive and sustained volcanism. The eruptions tap deep mantle sources with chemical signatures distinct from typical oceanic ridge basalts, suggesting that the Deccan represents a mantle plume event of extraordinary magnitude. The isotopic composition of the lavas documents crustal contamination processes that may have enhanced the toxic metal content of volcanic emissions. The interaction between Deccan volcanism and global climate systems creates feedback loops that amplify environmental instability. Volcanic cooling may disrupt monsoon patterns and oceanic circulation, while greenhouse warming from CO2 emissions interacts with orbital cycles to create complex climate variability. These interactions make it difficult to predict ecosystem responses and may explain why some groups show resilience while others collapse rapidly. The sedimentary record of the latest Cretaceous preserves evidence of increasing environmental instability in the form of more frequent storm deposits, altered river channel patterns, and changes in sediment composition that reflect modified weathering regimes. These geological indicators document landscape-scale environmental changes that occurred independently of any extraterrestrial impact. Mammalian communities show mixed responses to the Deccan volcanic stress, with some groups maintaining diversity while others suffer significant losses. The differential survival patterns may reflect differences in body size, dietary specialization, or physiological tolerance to environmental toxins. Small mammals with flexible dietary requirements appear to show greater resilience than larger or more specialized forms. The atmospheric chemistry modeling of Deccan emissions reveals the global scope of volcanic effects and their potential for triggering cascading ecosystem failures. Volcanic gases interact with existing atmospheric constituents to create novel chemical compounds and reaction pathways that have no modern analogues. The resulting atmospheric composition challenges the physiological limits of many organism groups while favoring others adapted to high CO2 or acidic conditions. As the Deccan volcanism reaches its crescendo in the final hundreds of thousands of years before the end Cretaceous boundary, Earth's biological communities face environmental challenges of unprecedented severity and complexity. The volcanic winter and greenhouse effects operate simultaneously to create climate conditions outside the range of previous geological experience. Ecosystems that had flourished for millions of years under stable greenhouse conditions find themselves subjected to rapid environmental changes that exceed their adaptive capacity. The stage is set for the final act of the Mesozoic era, as volcanic stress weakens the biological fabric of Earth's ecosystems and prepares them for the ultimate catastrophe that will end the age of dinosaurs. The bleeding Earth continues its volcanic hemorrhaging, each new lava flow adding to the environmental burden that will help determine which lineages survive to inherit the post-Mesozoic world. Only took a few 100,000 years of continental-scale volcanism to begin the process of environmental breakdown that will culminate in one of the great mass extinctions in Earth's history. The age ends not with violence, but with whispers. It is 66 million years ago, and the Mesozoic era draws toward its close not through the dramatic catastrophe that will soon follow, but through the gentle, inexorable processes that have shaped Earth's history for billions of years. Sea levels begin their gradual retreat from the continental highstands that had created the vast epicontinental seas of the Cretaceous greenhouse. Climate systems shift almost imperceptibly as atmospheric circulation patterns respond to changing continental configurations and the waning intensity of the Deccan volcanism. Evolution continues its patient work, unaware that time itself is running short for the giants that have ruled the Earth for 185 million years. The Western Interior Seaway, that great inland ocean that had divided North America for much of the Cretaceous, begins its slow withdrawal toward the ancestral Gulf of Mexico. This retreat occurs over hundreds of thousands of years, each generation of marine organisms adjusting to slightly shallower conditions, slightly different water chemistry, slightly altered current patterns. The vast carbonate platforms and mudstone deposits that accumulated during the seaway's maximum extent now emerge as coastal plains where terrestrial and marine ecosystems interface in complex transition zones. Ammonites, those spiral-shelled masters of Mesozoic seas, show their first signs of the decline that will lead to their extinction. Their diversity, which had reached extraordinary heights during the late Cretaceous, begins a gradual contraction as oceanic conditions shift away from the stable, stratified waters that had supported their explosive radiation. Species disappear one by one from different ocean basins, their extinction so gradual that it might seem natural rather than catastrophic to observers tracking the changes over geological timescales. The great reef systems built by rudist bivalves face their own quiet crisis as ocean chemistry responds to falling sea levels and continued volcanic outgassing from the Deccan province. These biological architects, which had created some of the most extensive carbonate platforms in Earth's history, find their calcification processes increasingly challenged by changing pH levels and altered carbonate saturation states. Individual reefs die back and are not replaced, creating gaps in the reef systems that will never be filled by rudest architects. Dinosaur communities continue their remarkable diversity, yet subtle changes appear in their species composition and ecological relationships. Some of the more specialized forms begin to disappear from the fossil record, replaced by more generalized species that may represent responses to increasing environmental variability. The intricate ecological relationships that had supported such high dinosaur diversity during the peak of the late Cretaceous show signs of simplification as environmental stress reduces the stability necessary for highly specialized interactions. Flowering plants maintain their evolutionary momentum, continuing to diversify and establish the ecological relationships that will dominate post-Mesozoic terrestrial ecosystems. Yet even among the angiosperms, some of the more specialized pollination relationships show signs of stress as insect communities respond to changing climate patterns and atmospheric chemistry. The co-evolutionary dance between plants and their insect partners continues, but with less precision than during the stable conditions of the earlier late Cretaceous. The polar forests that had thrived under greenhouse conditions begin to experience subtle changes in their seasonal rhythms as global climate patterns shift. The deciduous conifers that had adapted so successfully to months of darkness and continuous daylight show increasing variability in their growth patterns, their annual rings recording the climate instability that marks the final phase of the Mesozoic greenhouse period. Marine productivity in the global oceans shows regional declines as oceanic circulation patterns respond to changing continental configurations and sea levels. The massive coccolithophore blooms that had characterized Cretaceous seas become less frequent and extensive, while planktonic communities show increasing dominance by smaller, more opportunistic species adapted to variable environmental conditions. Continental weathering patterns shift in response to the combination of changing climate and the continued outgassing from Deccan volcanism. Enhanced chemical weathering rates alter nutrient delivery to marine systems while simultaneously buffering some of the atmospheric changes through increased consumption of atmospheric CO2. These processes operate over timescales of hundreds of thousands of years, their effects accumulating gradually rather than creating sudden environmental crises. The trace fossil record from latest Cretaceous sediments documents changes in animal behavior that suggest responses to increasing environmental variability. Burrowing traces become more complex and deeper, possibly reflecting attempts to escape increasingly harsh surface conditions. Dinosaur trackways show subtle changes in herd structure and migration patterns that may document behavioral adaptations to changing resource distribution. Small mammal communities show remarkable stability during this period of transition, their ecological flexibility and small body sizes providing resilience against environmental changes that challenge larger, more specialized organisms. The mammalian radiation that will characterize the Cenozoic era remains in the future, but the foundation for that explosion is being laid by the survival strategies developed during these final Mesozoic millennia. Ocean chemistry continues its gradual shift away from the extreme greenhouse conditions that had characterized much of the Cretaceous period. Deep water temperatures begin a slow decline as reduced greenhouse gas concentrations allow the first stirrings of the thermal gradients that will eventually drive Cenozoic oceanic circulation patterns. The transition occurs so gradually that individual generations of marine organisms experience conditions little different from their parents. Yet the cumulative effect represents fundamental changes in oceanic systems. Atmospheric composition shows the complex interplay between declining volcanic outgassing rates and the continued effects of enhanced continental weathering. Carbon dioxide concentrations remain far above modern levels, but show the first signs of the long-term decline that will characterize post-greenhouse climates. These changes occur over timescales that dwarf human experience, yet they represent rapid transitions in the context of Earth's long climatic history. The sedimentary record of the latest Cretaceous preserves evidence of these gradual transitions in the form of changing fossil assemblages, altered depositional patterns, and geochemical signatures that document shifting environmental conditions. Individual rock layers may appear monotonously similar, yet their subtle differences record the patient work of environmental change operating at the pace of geological time. Biogeographic patterns show increasing provincialism as falling sea levels eliminate some of the oceanic barriers that had promoted cosmopolitan distributions during the height of the Cretaceous greenhouse period. Continental faunas begin to develop more distinctive characteristics as intercontinental exchange becomes more limited, setting the stage for the endemic radiations that will characterize early Cenozoic biogeography. The co-evolutionary relationships between different organism groups continue their subtle adjustments to changing environmental conditions. Plant-herbivore interactions, predator-prey relationships, and mutualistic partnerships all show signs of the stress that accompanies environmental transition. Some relationships strengthen under stress, while others weaken and eventually dissolve entirely. As the Mesozoic era approaches its final moments, Earth has already begun the transition toward the very different world that will emerge from the coming catastrophe. The changes are gradual, almost imperceptible from the perspective of individual organisms, yet they represent fundamental shifts in the planetary systems that have supported Mesozoic life for nearly 185 million years. The gentle endings accumulate like sediment in a quiet lake, each small change contributing to transformations that will only become apparent when viewed across the vast perspectives of geological time. The age of reptiles draws toward its close not through sudden collapse, but through the patient work of environmental change operating at the stately pace of deep time. The whispers grow softer now, as if Earth itself prepares for sleep after the longest summer in its biological history. The giants still walk the ancient landscapes. The forests still grow toward greenhouse skies. The seas still teem with creatures whose evolutionary experiments have created some of the most spectacular life forms in planetary history. Yet, change moves through these systems like a gentle current, reshaping everything it touches while maintaining the appearance of continuity. The Mesozoic ends as it began, with the quiet persistence of life adjusting to changing conditions. The patient accumulation of small modifications that sum to revolutionary transformations. The endless creativity of evolution exploring new possibilities within the constraints imposed by physics and chemistry and the deep patterns of geological time. Only took 185 million years to create a world of giants, and now that world prepares to give way to something entirely new, its ending as gradual and inevitable as the changing of seasons in the vast year of deep time.